Mars looks close in the night sky, yet for a human crew it becomes a world of long silence, slow rescue, and strict orbital timing. A landing is only the beginning. Every day depends on power, air, water, and repairs that must work without quick help from Earth, while the return window waits months away and a single failure can stretch that wait into years. Tonight, this calm documentary follows the realistic science behind why the first humans on Mars may never return, not through drama, but through distance, logistics, and the fragile chain that makes a trip home possible. Before settling in, please like the video, subscribe to the channel, and let this quiet journey to the red planet carry the night gently forward. Mars hangs in the solar system as a nearby world in astronomical terms, yet it remains remote in human terms. Its reddish light is familiar in the night sky, and its orbit lies close enough to Earth that spacecraft can reach it with known physics and careful planning. Still, the space between the two planets is not a simple gap. It is a changing corridor, shaped by two moving orbits, two different speeds, and a sun that dominates every trajectory. This changing separation becomes the first quiet reason a human mission to Mars can drift toward permanence. Distance does not merely make travel longer. Distance reshapes responsibility, timing, and the meaning of rescue. Earth and Mars both circle the Sun, and they do so on different paths. Earth's orbit is closer in and faster. Mars's orbit is farther out and slower. Because of this, the two planets do not hold a fixed spacing. At some times, Mars is relatively nearer, appearing brighter and larger from Earth. At other times, it is far across the Sun's neighborhood, diminished to a small point. The physical distance spans tens of millions of kilometers at the near end and reaches hundreds of millions of kilometers at the far end. The exact number at any moment depends on where each planet sits along its orbit. For a crew, this changing distance is not an abstract fact. It shapes how long travel takes, how much energy is needed for different paths, and how long a spacecraft remains exposed to the hazards of deep space. The Sun fills the space between planets with invisible structure. Solar gravity sets the basic shape of every interplanetary path. Solar radiation and the solar wind fill the volume with energetic particles, magnetic fields, and a steady outward flow of plasma. Even before a vehicle leaves Earth's vicinity, the mission becomes part of this solar environment. A voyage to Mars is not a straight line. It is a careful fall and climb through the Sun's gravitational field, arranged so that a spacecraft arrives where Mars will be, not where Mars was. The reality of this geometry means that travel is always a compromise between energy, time, and mission capability. When a mission is designed for human life, the compromise is narrower because time and reliability matter as much as fuel. Distance also changes how Earth can support a crew. Near Earth, a spacecraft is never far from the possibility of rapid return. Supplies can be launched quickly, crews can be evacuated, and ground controllers can respond to emergencies with close communication and frequent updates. Mars breaks this pattern simply by being far away. A vehicle traveling between planets cannot be reached by a rescue craft in days. It cannot be supplied in a week. The crew carries what the mission brought and what the mission can produce locally. When a return depends on future hardware arriving on schedule, distance turns schedule into fate. The communication link is shaped by distance in a direct, physical way. Radio signals travel at the speed of light, and light requires time to cross the interplanetary gap. When Mars is relatively near, the delay is still long enough that conversation becomes staggered and guidance becomes delayed. When Mars is far, the delay becomes much longer. This is not a minor inconvenience. It changes the entire operational posture of a crewed mission. A crew cannot rely on immediate instructions from Earth during a fast-developing crisis. Ground teams can advise, but the crew must act first and explain later. This shift is not a matter of confidence, it is a matter of physics. The distance enforces autonomy. Autonomy becomes more than a psychological condition. It becomes a safety system. The crew must diagnose and repair faults without real-time coaching. The crew must manage medical events without evacuation. The crew must make risk decisions with delayed support. In the outer layers of the mission, this autonomy is already present during the cruise to Mars, where the spacecraft is a closed habitat moving through deep space. The more distant Mars is during any phase of the mission, the more absolute this autonomy becomes. Distance turns Earth from a controller into an advisor and, at times, into a distant archive of expertise that arrives too late for immediate action. The same distance also shapes the reliability demanded of equipment. A mission can accept certain kinds of failure when replacement is close. It cannot accept those failures when replacement is months away. Systems for air, water, temperature control, radiation monitoring, and power must operate continuously. Spares must exist in the habitat, and the crew must be able to install them. Tools and materials must be present for unexpected repairs. Every missing part becomes more important as the distance grows, because missing parts cannot be delivered quickly. Distance, therefore, increases the value of redundancy and the cost of every design choice. Distance affects the mission even before arrival, because a vehicle traveling to Mars is exposed to deep space conditions for a long time. Away from Earth's protective magnetic field, the spacecraft is more exposed to energetic particles, including galactic cosmic rays and bursts of solar particles. The longer the travel time, the more exposure accumulates. Distance does not only lengthen time, it increases the fraction of emission spent in the interplanetary environment. Even if a crew lands safely, the accumulated strain of the journey becomes part of what the crew brings to the surface. The mission's margin becomes thinner without any dramatic event. It is reduced by the slow arithmetic of exposure and wear. Distance also changes how failure is counted. On Earth, many failures are inconvenient. In orbit near Earth, many failures are serious but recoverable with assistance. Between planets or on Mars, certain failures can become irreversible because the path back is not immediately available. A damaged return vehicle cannot be replaced quickly. A loss of critical supplies cannot be repaired by an airdrop. A loss of power cannot be compensated by rapid resupply. Distance makes the mission more brittle, not because the hardware is weaker, but because the support network is farther away. This brittleness is one reason the first human missions to Mars are sometimes discussed as potentially non-returning, not as a chosen sacrifice, but as a risk shaped by logistics and physics. There is also a quieter point about distance and timing. The relative positions of Earth and Mars change continuously, and the energy required to travel between them depends on those positions. A return is not only a matter of having a vehicle, it is a matter of returning during a period when a feasible path exists for that vehicle's capabilities. This is a basic feature of orbital mechanics. When a crew lands on Mars, the possibility of return is already tied to future alignment, future travel time, and future energy cost. The mission therefore becomes a sequence of commitments, each one made under distance constraints that cannot be negotiated with determination or skill. Commitment is built into the geometry. Mars itself deepens the separation. The planet is smaller than Earth and has weaker gravity, which helps launch vehicles in one sense. yet it also has a thin atmosphere, which provides little protection from radiation and little buffering from temperature swings. A habitat on Mars must provide what the environment does not. That need increases reliance on technology, and the reliance is again shaped by distance, because any large replacement is not near. The planet is also far enough that there is no practical path for a rapid evacuation back to Earth, even if a crew can launch from Mars. The distance between planets means that returning is a full interplanetary voyage, not a short hop. This outermost framing does not claim that return is impossible. It establishes why return is never a simple promise. The first humans on Mars face a basic physical condition. The planet is not a nearby destination in the way a ship reaches an island. It is a moving world across an interplanetary gap that expands and contracts, and that gap imposes delays, exposure, and dependence on long logistics chains. If something fails at the wrong time, distance can turn a temporary setback into a long stay. If multiple setbacks align, distance can turn a long stay into permanence. The path to Mars begins with this truth. Before discussing equipment, landing systems, habitats, or fuel, the mission must be understood as a problem of separation governed by motion and light. From this outer region, the inward path now moves toward the time geometry of travel, where the changing Earth-Mars relationship creates strict opportunities and long waiting periods that can decide whether return remains feasible. The path between Earth and Mars is governed by timing as much as by propulsion. The two planets move on separate orbits, and their relative geometry creates windows when travel is efficient and windows when travel is costly or impractical for the same vehicle. This timing structure is sometimes described as a launch window, yet the phrase can feel too small for what it represents. A launch window is not merely an opportunity to depart. It is a schedule that shapes the entire mission, including how long the cruise lasts, how long a crew must remain on Mars before a return becomes feasible, and what options exist if plans change. The clock of orbital mechanics becomes a quiet reason a first crew might remain longer than intended and, under some failure modes, might not return at all. Earth catches up to Mars and passes it in a repeating cycle because Earth orbits faster. This repeating cycle is called the synodic period, the time between similar Earth-Mars alignments. It is roughly a little over 2 Earth years. Within that cycle, there are intervals when a transfer from Earth to Mars can be achieved with comparatively low energy, using an orbit that intersects Mars's orbit at the right time. This simplest efficient transfer is often described as a Hohmann transfer, a trajectory that uses an ellipse tangent to Earth's orbit at departure and tangent to Mars's orbit at arrival. Real missions may use variations, but the key point remains. Efficiency comes from riding the natural geometry rather than forcing a direct chase. A human mission must balance efficiency with time and with risk. A slower, lower energy trajectory can reduce propulsion demands but increases time spent in deep space. A faster trajectory shortens travel time but demands more energy and can increase heat loads on spacecraft systems, as well as constraints on launch capability. These trade-offs matter for crew safety and for mission mass. They also interact with the launch window. The exact departure date within a window affects the achievable travel time and energy requirement. The window is not a single day. It is a span with a best region and less ideal edges. A mission architecture may be built around that best region, leaving less margin if delays occur. Launch windows also appear on the return side. A crew on Mars cannot simply depart whenever the return vehicle is ready. Earth and Mars must be in an alignment that allows a feasible transfer back. The same solar gravity that shapes the outbound path shapes the inbound path. For a typical mission that minimizes energy, the return opportunity comes after a waiting period on Mars. That waiting period can be long, often on the order of many months, because Earth must move into a position where the return transfer intersects Earth's orbit at the right time. This creates a mission that is not just travel and arrival, it is travel, arrival, long stay, then travel again. The long stay is not optional in many efficient mission designs. It is built into the geometry. This is why missed windows matter so much. If a critical element for return is not ready by the departure opportunity, the crew may have to wait for the next opportunity, which arrives roughly one synodic period later. That means a delay can be measured not in days or weeks, but in years. In the context of a Mars surface mission, years are not just calendar time, they are life support time, maintenance time, radiation exposure time, and psychological time. A crew can survive a delay if the habitat and supplies can support it. A crew can also be pushed beyond planned capacity if the delay extends the mission beyond the design life of key systems. The window structure is therefore a multiplier of small failures. A minor delay in cargo delivery can become a major risk if it pushes a schedule past a departure opportunity. A minor issue with a return vehicle can become a long-term problem if it cannot be corrected before the window closes. On Earth, repair teams and spare parts can be summoned. On Mars, the inventory is finite, and the time to send new hardware is measured in months to years. If a return vehicle is damaged beyond repair after landing, and if no second return vehicle is present, the next chance depends on launching and landing an entire new vehicle on a later window. This is a large logistical demand and may not be feasible in time to matter. Some mission concepts reduce the waiting time by using higher energy trajectories, sometimes described as opposition class trajectories, where the overall mission duration can be shorter, but the energy requirements are higher, and the return path may pass closer to the Sun. Other concepts accept a longer total mission with a long surface stay, sometimes described as conjunction class missions, which minimize energy but require the crew to remain on Mars until the planets align again for the return. Each approach carries risk. The higher energy approach reduces time on Mars but can increase spacecraft mass requirements and expose the crew to different thermal and radiation conditions. The lower energy approach reduces propulsion demands but increases the time a crew must maintain a functioning outpost with no resupply beyond what can be landed during the same campaign. The key point is that the return is not a simple reversal. It is a second interplanetary mission with its own launch window, its own travel time, and its own exposure. A crew can be healthy upon arrival and still face a long wait before a return can even begin. The surface stay becomes the dominant portion of the schedule, and the return window becomes the hinge on which everything turns. If the habitat's power system fails late in the stay, the crew cannot simply leave the next day. The window may still be months away. If the return vehicle requires a fuel production campaign on the surface, that campaign must complete before the window. If it does not, the crew waits for the next window, or the return becomes impossible. Waiting periods also intersect with seasonal and environmental conditions on Mars. Dust storms, cold seasons, and reduced sunlight can affect power generation and operations. The launch window itself does not care about dust, but hardware does. A return that depends on solar power to run life support and fuel production must survive the worst expected dust conditions during the waiting time. A delay that shifts the schedule into a more challenging season can increase risk, even if the orbital window remains open. The crew becomes tied to two calendars at once, the orbital calendar and the environmental calendar. Abort options are limited by the same geometry. In early phases of travel, There are certain trajectories that allow a spacecraft to swing past Mars and return to Earth without landing, sometimes called free return paths. These can serve as a safety concept if something goes wrong before arrival. Yet such paths still take time and still require a spacecraft capable of sustaining life support for the full loop. Once a crew commits to landing, the nature of abort changes. Leaving Mars requires an ascent vehicle that works, and then an interplanetary vehicle that can depart on an appropriate trajectory. A problem that occurs on the surface cannot always be solved by immediate departure. If an ascent vehicle is not ready, or if Earth is not in a favourable position, the abort becomes a wait, not an escape. This geometry also drives the logic of pre-deployment. Many realistic mission plans require that key return elements arrive before the crew. A return vehicle can be landed in advance. Power systems can be established in advance. Supplies can be stacked in advance. This reduces the chance that a crew arrives to an incomplete base. Yet pre-deployment itself is limited by windows. Cargo missions must also use Earth-Mars transfer opportunities. If a cargo mission fails to land or lands too far from the planned site, correcting that error can take years. If multiple cargo elements fail in a single campaign, the crewed mission may be delayed by an entire synodic cycle. This delay can strain budgets and programs, and it can change political support in a realistic context. Program continuity becomes part of mission feasibility, because windows do not pause for changing priorities. The possibility that the first humans on Mars may not return is therefore not primarily a story of a single catastrophic event. It is a story of alignment and delay. A mission can survive many problems if it can return quickly. Mars missions do not allow quick return. They allow return at specific times. Between these times, the crew must endure with what is present. If the return hardware fails and cannot be repaired, the crew's fate becomes tied to whether a new return capability can be delivered in a later window. That delivery is a major endeavour, and in the early era of human Mars travel, the system may not have redundancy or rapid repetition. The first mission architectures may be close to the limit of what can be launched and assembled. In such a context, a missed return window is not merely a schedule slip. It can become a fundamental change in outcome. This region therefore establishes the orbital clock as a structural constraint. Earth-Mars windows determine when departure is efficient, how long travel lasts, and when return is feasible. Waiting periods on Mars are not optional in many realistic mission designs. Delays can compound into years. Aborts become waits. Rescue becomes a future window rather than a near response. With this timing framework set, the inward path moves toward another form of separation that follows from distance, but has its own consequences. The communication delay that limits real-time support and forces operational autonomy during travel and on the surface. Between Earth and Mars, communication is limited by a simple constant. Radio signals travel at the speed of light, and light needs time to cross interplanetary space. This creates a delay that no engineering can remove. The delay varies as the distance between the planets changes, but it always exists, and it is long enough to reshape mission operations. In near-Earth space, controllers and crews can exchange information rapidly and correct mistakes quickly. On a Mars mission, information arrives late, advice arrives late, confirmation arrives late. A crew becomes the first responder to every problem, because the first response must happen before Earth can reply. The one-way delay is the most direct constraint. When Mars is relatively nearer, the delay is still measured in minutes. When Mars is farther, it is measured in tens of minutes. A round-trip exchange therefore takes twice that time, plus the time required to interpret and compose messages on each end. This means that a back-and-forth conversation about a malfunction cannot proceed as it would in a control room linked to a low Earth orbit mission. A question sent from the crew does not yield an immediate answer. A suggestion from Earth cannot be applied instantly, and then corrected instantly if it is wrong. The mission must be structured so that the crew can act without waiting for confirmation. Communication delay does not simply slow decision-making, it changes responsibility. In a fast-moving emergency, the crew cannot depend on ground team to diagnose and guide every step in real time. The ground can send procedures and expertise, but the crew must interpret local conditions and choose actions under uncertainty. This requires autonomy in a practical sense, the ability to detect faults, isolate causes, execute repairs, and manage risks without immediate outside input. Autonomy also includes the ability to refuse a remote instruction if local conditions make it unsafe. The delay forces this, because the people on Earth do not experience the situation directly, and their view is always older than the present moment on the spacecraft or on Mars. The delay also reshapes how plans are written. A Mars mission cannot rely on constant interactive direction. It relies on pre-planned timelines, checklists, and decision trees that anticipate likely failures and specify what to do first. These documents must be detailed and must be designed for use under stress and fatigue. They must also allow flexibility. A rigid script can fail if a malfunction does not match the expected pattern. Therefore, the plan must include principles and diagnostic methods as well as step-by-step actions. This is a different planning style than a short mission with rapid ground support. It is closer to the planning style of deep-sea operations or remote field expeditions, where local teams must solve problems with limited contact. Bandwidth and coverage add additional constraints. Communication with distant spacecraft depends on large antennas and networks such as the Deep Space Network. Time on these antennas is shared among many missions. Scheduling must be arranged, and continuous coverage is not guaranteed. A crewed mission would receive high priority, yet the physics of the Earth's rotation and the geometry of ground stations still create limits. There can be times when a spacecraft is not in view of a station, or when signal quality is reduced. Mars itself can block line of sight when the geometry places the Sun between Earth and Mars. This configuration, known as solar conjunction, can degrade or interrupt communication because radio signals pass near the Sun and are disturbed by solar plasma. During conjunction, communication becomes less reliable and may be limited to essential data or paused for safety. This is a predictable interval, but it adds a period when autonomy must increase even further. The delay also affects situational awareness. A crew in transit or on the surface has sensors and cameras, but transmitting high volumes of data continuously may not be practical. Compression can reduce quality. Limited bandwidth can force prioritization, where essential telemetry is sent and less critical data waits. Some scientific and maintenance data may be stored and transmitted later. As a result, Earth-based teams often operate with partial information. Their understanding of a system's state can lag behind the crew's direct experience. This makes it harder for Earth to provide timely, precise guidance during evolving faults. The mission must therefore assume that Earth will sometimes be behind and that the crew's judgment is the most current data source. Autonomy is not only human, it is also software and hardware. A spacecraft must detect failures and react quickly without waiting for commands. This includes fault detection, isolation, and recovery systems that monitor pressures, temperatures, power flows, and atmospheric composition. Then trigger safe modes when thresholds are exceeded. A safe mode is a pre-programmed state that reduces activity and protects critical systems. In near-Earth operations, safe mode can be an inconvenience because controllers can intervene quickly. On a Mars mission, safe mode must be designed so that it protects life support and does not create new hazards. A deep space vehicle must manage its own thermal balance, power distribution, and attitude control in a way that remains safe for a crew. A key operational shift occurs in how decisions are distributed. Some decisions are delegated to onboard automation because they must happen faster than any human can respond, such as rapid power switching during a fault or attitude adjustments to maintain thermal constraints. Other decisions are delegated to the crew because they require context and trade-offs, such as whether to shut down a system that is behaving unpredictably, whether to perform a risky repair, or whether to conserve supplies at the cost of reduced comfort. Earth-based teams retain a role in longer horizon planning, analysis, and strategy, but the crew becomes the owner of immediate survival decisions. This distribution must be explicit, because ambiguity about who decides can waste time and increase risk. Communication delay also changes medical operations. A Mars crew can consult with physicians on Earth, but the guidance arrives late. In an acute medical event, the crew must stabilize the situation before detailed advice arrives. Remote medicine, therefore, becomes an asynchronous system. The crew sends data, performs initial care, and receives recommendations that may apply to ongoing management rather than immediate response. This makes training and onboard medical capability more important. It also increases the need for diagnostic tools and for protocols that can be executed without specialist presence. The same constraint appears in engineering. Troubleshooting becomes a local skill set supported by remote expertise, not directed moment by moment from afar. The delay changes the meaning of psychological support as well. A crew cannot rely on continuous conversation with Earth. Messages become delayed and sometimes scheduled. The social sense of being connected is weaker. This can increase feelings of isolation, especially during stressful periods when support is needed most. A realistic mission must plan communication routines that maintain connection despite the delay, using recorded messages, scheduled conferences, and structured information exchange. Yet even with such planning, the delay remains. The crew lives in a different time frame than mission control, with responses arriving after the moment has passed. The delay also increases the importance of onboard knowledge. A crew cannot treat Earth as an instant library. Technical manuals, spare part lists, repair procedures, and scientific references must be available locally. Digital libraries must be robust and redundant. Training must be deep enough that crew members can apply principles rather than memorize scripts. The mission must be able to improvise within safe boundaries when a problem does not match a prepared case. This is a subtle but central reason why early Mars crews face elevated risk. The environment demands a blend of expertise, discipline, and adaptation that is difficult to test fully on Earth. The communication system itself becomes a critical life support element. Antennas must work, power must support transmission, pointing must remain accurate. Dust on Mars can affect surface antennas and equipment. Mechanical wear can degrade moving parts. Software errors can interrupt protocols. Each failure mode matters more at Mars distance because remote troubleshooting is delayed. If communication is degraded, Earth cannot monitor the crew's status as effectively, and the crew cannot access remote advice and coordination. A crew can survive a temporary loss of communication, but extended loss increases risk and increases uncertainty about what help might arrive later. Communication delay therefore becomes a structural force. It encourages mission designs that are robust against failure, because rapid remote intervention is not available. It encourages redundancy, because replacing a failed system is slow. It encourages autonomy, because immediate decisions must be made locally. It encourages careful planning, because improvisation has limited support. It also changes the cultural model of human spaceflight. Instead of a tightly supervised operation, a Mars mission becomes a remote expedition where Earth is present as delayed guidance and long-term strategy, while the crew handles the immediate reality. In this region, the logic remains calm and direct. The distance between Earth and Mars introduces a light time delay that prevents real-time control. Coverage limits and solar conjunction can reduce communication further. Bandwidth constraints limit continuous high-fidelity data flow. These factors make autonomy a safety requirement. Autonomy is expressed through onboard fault management, crew training, local decision authority, robust procedures, and deep onboard knowledge. The result is a mission posture where the first humans on Mars cannot rely on immediate rescue or immediate instruction. They must sustain their own systems and their own decisions across delays that are built into physics. Arrival at Mars is not the end of a journey. It is a transition through a narrow band of physics where a crew and their cargo must survive heat, speed, and uncertainty in minutes. The phrase entry, descent, and landing describes this transition. Yet the calm reality behind it is stark. A spacecraft approaches Mars with interplanetary velocity. It must shed most of that energy without the thick atmospheric cushion that makes Earth re-entry more forgiving for large vehicles. Mars has an atmosphere, but it is thin. It can burn off energy and provide lift, yet it cannot slow heavy masses to a safe touchdown on its own. This creates a central constraint for human missions. A large crew and the equipment required for a safe return demand heavy payloads. Heavy payloads are the hardest to land. This difficulty shapes the entire architecture of whether return remains possible. A Mars-bound vehicle arrives fast. Its energy is set by the trajectory from Earth and by Mars's gravity as it falls inward. The energy must be removed by interacting with the atmosphere and by using propulsion. Atmospheric entry uses drag, the resistance of air to a moving body, and it converts kinetic energy into heat. On Earth, thick air provides strong drag. On Mars, thin air provides less. The vehicle still heats during entry, because high speed through even thin air produces intense compression and heating. A heat shield must protect the vehicle from this heating. Yet the thinness of the atmosphere means the vehicle spends less time in dense air and cannot rely on drag alone to slow down enough for landing. Heat and insufficient slowing arrive together as a design problem. Descent then becomes a controlled fall through an atmosphere that can help, but not enough. Parachutes work in air, and they have been used successfully for robotic landers. Yet parachutes depend on atmospheric density to generate drag, and their size grows quickly as payload mass increases. For very heavy payloads, parachutes become enormous, difficult to deploy reliably, and limited by material strength and by the dynamics of opening. At the same time, the speed at which a heavy vehicle must be slowed remains high. In the thin Martian air, even large parachutes may not reduce speed enough for a safe touchdown. This pushes missions toward propulsion for final descent, using engines to brake and to land softly. Propulsive landing introduces its own limits. Engines require fuel. Fuel adds mass. More mass is harder to slow during entry. The mission therefore faces a coupled loop. A heavier lander needs more braking capability. More braking capability increases lander mass. The atmosphere cannot provide enough braking for heavy landers, so engines must do more work, and that work demands still more fuel. This loop is manageable for small robotic landers. It becomes very difficult as payload mass rises toward the scale needed for human habitats, large life support systems, and a return vehicle. The landing problem is not only about mass, it is also about precision. A crewed mission needs to land near pre-deployed supplies, power systems, and habitats. A landing far from these assets can turn a planned base into an unreachable set of separate islands across a hostile landscape. Mars terrain includes rocks, slopes, dust, and cratered surfaces. Safe landing requires hazard avoidance and careful site selection. Robotic systems can avoid some hazards, but the demands increase for larger vehicles. A large lander has less tolerance for uneven ground. Its legs or landing system must handle loads reliably. Its descent plume can blow dust and small rocks, affecting visibility and potentially damaging nearby equipment. The more massive the lander, the more powerful the engines required for final braking, and the stronger the interaction with the surface. Communication delay adds to the landing challenge. A Mars landing cannot be flown by real-time joystick from Earth. Commands arrive late. The landing must be autonomous or crew-guided on board, using sensors and pre-programmed logic. Autonomy must handle unexpected wind, unexpected dust, and unexpected terrain. It must manage the transition between entry heating, parachute or drag device deployment, and engine ignition. A small error in timing can be fatal. A sensor fault can lead to a wrong altitude estimate. A parachute deployment failure can leave too little time for engines. A guidance error can bring the vehicle down in an unsafe area. These are rare events, but the margins are small, and heavy payloads tend to narrow margins further. Landing heavy cargo is also difficult to repeat. A robotic lander failure is a loss of money and schedule. A crewed lander failure is a loss of life. Because the risk is high, realistic mission plans generally require that cargo is landed first, before crew arrival, habitats, power systems, and return hardware are placed on the surface in advance. This reduces crew risk, but it transfers criticality to the cargo landing campaign. If cargo does not arrive, the crew cannot go. If cargo arrives damaged, the mission must adapt. If cargo arrives far from the target, the mission may become impractical. Each cargo landing is therefore a gate that must be passed. The more cargo that is needed, the more gates exist. Each gate carries the full complexity of entry, descent, and landing in the thin Martian air. The return problem is shaped directly by this. A mission that intends to bring people home must land a return system, or the means to build one. That system includes an ascent vehicle and the fuel required to launch from Mars. Fuel is mass. Ascent hardware is mass. Landing that mass is difficult. A mission can attempt to produce propellant on Mars using local resources, such as carbon dioxide from the atmosphere and water from ice deposits. But the equipment for this production is itself mass and must be landed. The production must then run reliably for months to fill tanks. If the production system fails, the return fuel may not exist. If the return vehicle is damaged during landing, the mission can lose the path home. Entry, descent, and landing therefore becomes one of the strongest single links between a planned round trip and a mission that becomes one way by circumstance. Mars weather adds complexity without providing safety. The atmosphere is thin, but it carries dust. Dust can reduce visibility during descent and can alter solar power after landing. Dust storms can cover large regions and can persist. The wind speeds associated with storms may not be extreme in terms of force because the air is thin, but dust can still create optical hazards for sensors and cameras. A landing system that relies on vision-based navigation must operate in dusty light. A landing system that relies on radar must cope with scattering and surface reflectivity. These are solvable problems, but they must be solved with high confidence because the landing happens once and cannot be paused. The thin atmosphere also creates a peculiar operational region where the vehicle is too high for parachutes to be fully effective and too low to ignite engines casually. This is a transition zone where the vehicle must make rapid choices. Robotic missions have shown that this zone can be managed for small craft. Scaling up requires that guidance, thermal protection, and propulsion are integrated at a higher level of complexity. The vehicle must survive high heating loads, maintain stability, deploy drag devices reliably, and ignite engines at the right time with the right thrust. Any system that fails in sequence can cascade. A late engine start can lead to impact. A wrong attitude can lead to loss of control. A heat shield breach can lead to structural failure. The crewed mission must treat these as engineering facts rather than as dramatic possibilities. Landing also affects the base environment after touchdown. A large lander can raise dust that settles on solar panels and radiators. It can erode nearby surfaces. It can blow loose material into equipment. Therefore, the base layout must consider plume effects and downwind dust deposition. Landing pads may be needed, which implies construction, which implies equipment, which implies more landed mass. Each solution adds requirements. Requirements add cargo. Cargo adds landing demand. This is another loop that makes early mission planning conservative and that pushes designs toward fewer, larger landings, which in turn increase the consequence of any single failure. The risk profile of entry, descent, and landing is also different from most other mission phases. Cruise phases allow time to diagnose and repair. Surface phases allow time to work, though within environmental constraints. Entry, descent, and landing compresses decisions into a short interval. There is limited time for correction. Systems must work as designed. This creates a psychological and operational reality. The mission can be robust for months and still be lost in minutes if landing fails. For the question of return, this means that even if the crew lands safely, the return hardware must also land safely. Whether it arrives with the crew or earlier, if a return vehicle fails to land or fails after landing, return becomes a future problem rather than a guaranteed phase. This region therefore connects directly to the title's realism. The first humans on Mars may not return not because Mars is a mystical trap, but because the mission's heaviest and most critical components must survive a landing process that is still difficult at large scale. The thin atmosphere provides too little braking for heavy payloads. Parachutes have scaling limits. Engines demand fuel that increases mass. Precision landing is necessary for a base. Autonomy is required because Earth cannot steer in real time. Cargo must arrive before crew, multiplying the number of high-stakes landings. A failure in any of these can remove return capability and convert a planned round trip into an extended stay. From this arrival constraint, the inward path moves toward what must exist on the surface before a crew arrives, because the landing limits determine how much can be delivered, how often delivery can be repeated, and how vulnerable the chain becomes when any essential element fails to arrive intact. A crewed Mars mission is rarely built as a single flight with everything inside. The realistic architecture assumes that the first human habitat is assembled by a chain of earlier deliveries, each one landing supplies, power equipment, and critical systems before any crew departs Earth. This pre-deployment approach is not a preference for convenience. It is a response to distance, timing windows, and the thin margins of life support. When the first humans arrive, the base must already exist in functional form, because the surface environment does not allow a gradual settling in with easy resupply. If any essential element fails to arrive, arrives damaged, or arrives too far from the target site, the mission can slide toward a state where return depends on waiting and improvisation rather than on a planned sequence. Pre-deployment begins with a simple logic. The mass required to keep people alive on Mars is large. A habitat must hold pressure, manage carbon dioxide, produce or store oxygen, recycle water, control temperature, and provide shielding against radiation and dust. It must include tools, spares, and redundancy. It must include medical supplies and the capacity to treat injuries and illness without evacuation. It must provide food storage and, if crop growth is planned, lighting, water management, and controlled atmosphere for plants. It must provide communications and navigation systems. Each category adds weight and volume. Entry, descent, and landing constraints limit how much mass can be placed on the surface in one attempt. Therefore, the base emerges from multiple cargo landings. Each landing becomes a dependency that must succeed for the crewed phase to remain feasible. Power is usually among the first dependencies. Without stable power, life support and communications fail, and no later assembly can proceed safely. A cargo mission may deliver solar arrays, power storage, and power distribution hardware. Another cargo mission may deliver a nuclear power unit if that is part of the design. Either approach has consequences. Solar power is vulnerable to dust accumulation and to long periods of reduced sunlight. Nuclear power reduces dependence on sunlight but adds complexity, mass, and heat management needs. In either case, power equipment must survive landing and then operate reliably for long periods before the crew arrives. This means the equipment must function unattended or with limited robotic assistance, because a crew is not yet there to repair faults. A power system that requires frequent maintenance is not suitable as an unmanned precursor. Therefore, pre-deployment forces an early test of reliability in the harsh surface environment. Habitats are another dependency. A crew cannot arrive to a plan that expects building a pressurized home from raw parts in the open air. The habitat must be present, sealed, and capable of maintaining internal pressure before people commit to landing. Many designs therefore assume a landed habitat module that can be checked remotely, pressurized, and monitored. Sensors can report pressure stability, internal temperature, and air composition, yet sensors do not guarantee habitability. A small leak can be tolerable in short missions and catastrophic over months. The habitat must be robust to dust intrusion at seals, to temperature cycling that stresses materials, and to micrometeoroid impacts that can puncture thin walls over time. Pre-deployment means the habitat must survive alone for a long interval, exposed to the environment, and still be safe when the crew arrives. Supplies and spares must also be on the ground in advance. Many mission risks come from small failures that become unrepairable when a specific component is missing. Filters clog, pumps fail, valves stick, electronics degrade under radiation. A base must include spare parts for the most likely failures and tools to replace them. Pre-deployment allows these spares to be delivered early, but it also introduces new failure modes. Cargo can land far from the main habitat, making retrieval difficult. Cargo can be damaged by impact or by dust intrusion. Cargo packaging can degrade during long exposure to ultraviolet light and temperature extremes. If a critical spare part is lost in a failed landing, replacing it can take an entire Earth-Mars launch cycle. The mission then becomes a long wait for recovery, during which the base may slowly degrade. Pre-deployment is also shaped by the return requirement. A mission that intends a return must deliver either a return vehicle itself or the means to fuel and support that vehicle. A return vehicle must be protected from dust, thermal cycling, and mechanical wear during the entire surface stay. It must be able to start and function after months of exposure. If the return vehicle lands in a separate mission ahead of the crew, it must remain healthy through the waiting period before the crew arrives, and then remain healthy through the crew's entire surface stay. This is a long-duration demand on a complex system. If the return vehicle arrives damaged or cannot be checked adequately, the crewed mission cannot proceed without accepting a severe increase in one-way risk. Many realistic mission concepts include in-situ resource utilization, the production of useful materials from local resources. The most discussed example is propellant production using Mars's carbon dioxide atmosphere and water extracted from ice. This is attractive because hauling return fuel from Earth is extremely mass expensive. Yet the production equipment itself is complex and must operate for long periods with minimal maintenance. It requires power, chemical processing, pumps, compressors, storage tanks, valves, and controls. It requires cold-resistant operation and dust-tolerant intakes and seals. It must produce propellant at the right purity and store it without loss. If the propellant plant fails, return fuel may not exist. This makes in-situ propellant production a central gate in the mission. A cautious architecture therefore demands that the production plant be landed and run successfully before a crew is committed. The base must prove it can make and store propellant, not merely promise it. Pre-deployment also demands a stable landing site strategy. Cargo must land close enough to be useful. Precision landing at human mission scale is not trivial, and dispersion across the surface can turn a base into scattered assets. Retrieval across kilometers of rough terrain in a pressurized rover consumes time, power, and risk. In early missions, surface mobility may be limited. Roads do not exist. Dust and rocks complicate travel. Therefore, the landing ellipse, the area where a lander might touch down, must overlap significantly with the base zone. This requires advanced navigation and hazard avoidance. It also requires an acceptance that some landings may still miss the target. The base plan must either tolerate dispersion through robust mobility or reduce dispersion through better landing control. Both choices increase system complexity. Time windows multiply the vulnerability. Cargo missions and crew missions share the same orbital opportunities. If a cargo mission fails, there may be no chance to replace that cargo until the next window. This can push the crewed mission back by years. In an early program, long delays can threaten continuity of funding and political support. This is not a commentary on intention. It is a practical factor. Large interplanetary missions require sustained support across multiple years. A long delay can interrupt supply chains, change contractors, and alter priorities. Pre-deployment therefore introduces a programmatic fragility in addition to a technical one. The base must not only be built, the building process must survive setbacks without collapsing as a project. Autonomy matters again on the surface because much of the pre-deployed hardware must operate unattended. A habitat may need to maintain thermal control. Batteries may need to stay within temperature limits. Propellant plants may need to cycle through startup and steady operation. Communication relays must remain active. If a system enters a fault state, remote operators on Earth can diagnose, but their commands arrive with delay and with limited coverage. If a system requires physical intervention, no humans are present. Robots may help, but robotic dexterity and reliability on Mars remain limited, especially for complex repairs. Therefore, Pre-deployment demands that systems be designed for long unattended operation or for safe dormancy until crew arrival. This is where the possibility of non-return begins to take shape in a realistic way. A crew may land only after a base appears functional, but functionality can change over time. A small leak can grow, a dust-covered power system can degrade, a propellant plant can run well for months and then fail. If these failures occur after the crew arrives, the crew may be unable to restore full capability, especially if the failure requires a replacement part that is not present. A return plan that depends on a chain of pre-deployed systems can therefore break at a weak link. When it breaks, the mission does not end. It becomes a longer stay with fewer options, because the next replacement opportunity is tied to a distant launch window. Pre-deployment is still the most realistic approach for safety, because it reduces the chance that a crew lands to nothing. Yet it also creates a mission whose success depends on many landings and many systems working over long periods. Each dependency is a potential point where return capability can be lost without a dramatic single disaster. A crew can survive on Mars for months if the habitat and power remain stable. Return requires more than survival. It requires propellant, a functioning ascent vehicle, a healthy interplanetary vehicle, and the correct timing window. Pre-deployment determines whether those elements exist at all when the time comes. This region therefore completes a quiet shift inward. The mission is no longer described by distance alone or by landing physics alone. It becomes a system of systems problem. The first base must be present before humans arrive, because the surface environment does not allow slow assembly under uncertainty. That requirement creates a chain of cargo deliveries, each one subject to landing limits, dispersion, and failure. It also creates a dependence on long-duration unattended reliability for power, habitats, and propellant production. A missing element can delay a mission by years, and a failure after arrival can remove the planned return capability. In this way, pre-deployment, meant to reduce risk, also defines how a realistic mission can quietly become non-returning if the chain breaks and cannot be repaired before the next distant opportunity. On Mars, survival is not supported by the environment, it is supported by machinery and routine. The air outside is far too thin to breathe and far too cold to ignore. The pressure is low enough that unprotected bodily fluids would boil, and the temperature swings can stress materials and systems every day. Dust enters moving parts and settles on surfaces. The sunlight is weaker than on Earth, and the atmosphere provides little thermal buffering. A human habitat must therefore function as a small artificial world. It must maintain pressure, oxygen, temperature, humidity, and cleanliness continuously. This everyday requirement is a central reason the first humans on Mars may never return. The mission's return capability depends on the crew staying alive and the systems remaining functional for many months, sometimes more than a year, without resupply. Small failures become long problems because the environment offers no margin. Mars's atmosphere is dominated by carbon dioxide, with only traces of oxygen and water vapor. Its density near the surface is low compared with Earth's. This means air does not provide much convective heat transfer. A suit or habitat surface loses heat primarily by radiation rather than by air movement. It also means aerodynamic drag is weak, which affects both landings and the way wind interact with objects. Winds can be fast in speed, yet carry limited force. Even so, wind can lift and transport fine dust, and dust is a persistent operational hazard. Dust can infiltrate seals, it can coat radiators and reduce heat rejection, it can cover solar panels, it can scratch visors and optical sensors. Over time, Dust is less like weather and more like corrosion, a constant slow pressure on reliability. Pressure is the first non-negotiable boundary. A habitat must remain sealed, a suit must remain sealed, a rover must remain sealed if it is pressurized. Leaks are therefore a primary risk, and the risk increases with time because seals age and materials fatigue. Thermal cycling on Mars is strong because nights are cold, and days can be less cold but still below comfortable levels. Materials expand and contract. Small cracks can grow. Impacts from micrometeoroids are rare but possible, and even tiny punctures can matter in a low-pressure environment. The habitat must monitor pressure continuously, isolate compartments if needed, and have repair capabilities for punctures and seal failures. The crew must also manage airlocks, which are frequent leak sources because they cycle between pressure states. Temperature control is another constant requirement. Outside temperatures can drop very low at night, and daytime temperatures can remain below freezing in many locations. A habitat must provide heat continuously. It must also manage heat produced internally by equipment and by people. The thin atmosphere reduces convective cooling, so radiators must radiate heat to space. Radiators can be coated by dust, reducing their effectiveness. A reduction in heat rejection can lead to overheating of electronics and life support machinery. At the same time, power shortages can lead to insufficient heating, threatening freezing of water lines, failure of batteries, and reduced efficiency of chemical systems. The base therefore lives on a narrow thermal balance. It must keep systems warm enough to function and cool enough to avoid damage, all while the outside air offers little help. Mars also imposes a pressure on time and routine. Every excursion requires a suit or a pressurized rover. Suits are complex machines. They manage pressure, oxygen, carbon dioxide removal, water cooling, and power. They include seals, joints, and visors that can degrade under dust abrasion. They require maintenance and cleaning. If suit reliability declines, the crew's ability to work outside declines, and external tasks such as repairing power systems or deploying equipment become harder. In early missions, the base will likely depend on external work for maintenance, resource extraction, and construction. Therefore, suit system health becomes tied to return capability. Because return requires the crew to maintain the base, maintain the propellant system, and maintain the ascent vehicle. The Martian surface also carries chemical hazards. Dust can contain fine particles that are harmful if inhaled, and it can contain reactive compounds that complicate handling. A habitat must keep dust out or trap it at the airlock. It must filter air. Filters clog over time. Filter replacement requires spares. The base must also manage waste and hygiene to prevent microbial growth and contamination inside the habitat. A closed environment accumulates trace chemicals from plastics, lubricants, and human metabolism. Air scrubbing systems must remain effective. When such systems degrade, comfort decreases first, then health risk increases. In a place where evacuation is not possible, these degradations matter more. Water is essential and heavy. A Mars mission must recycle water aggressively. Water is used for drinking, food preparation, hygiene, and potentially for oxygen production if electrolysis is used. Water is also valuable for radiation shielding because hydrogen-rich materials reduce certain radiation exposures. Mars may have accessible ice in some regions, but extracting it requires equipment and energy and reliable operation. Early crews are likely to rely on stored water and recycling, with ice extraction as a goal rather than a guarantee. If recycling efficiency drops or a leak occurs, the water margin shrinks, and the crew must reduce consumption. Reduced hygiene can increase infection risk. Reduced water intake can degrade health. These are slow pressures that compound over time. Oxygen supply is managed by storage and recycling as well. A habitat can store oxygen tanks for initial periods and use chemical or mechanical systems to recover oxygen from carbon dioxide or from water. Carbon dioxide removal is continuous because humans exhale it constantly. On the International Space Station, carbon dioxide removal systems have been managed with redundancy and resupply. On Mars, resupply is slow. The systems must operate with high reliability for long periods. A failure that cannot be repaired becomes a mission-ending threat, and not in the sense of ending a schedule. It can end survival. Mars' gravity is lower than Earth's, which reduces weight and changes muscle loading. Low-gravity environments can lead to bone density loss and muscle atrophy. The crew will need exercise equipment to maintain health. Exercise equipment is not a luxury. It is a countermeasure. It consumes space, power, and maintenance. On Mars, the crew will also be exposed to a different daily rhythm. A Martian day is slightly longer than an Earth day. This difference can disrupt sleep and schedules. Over months, sleep disruption can affect cognitive performance and mood. In a closed habitat where mistakes can be fatal, cognitive performance matters. Dust storms can reduce solar power and increase operational difficulty. Even if winds do not exert large forces, reduced sunlight can last for days or weeks in certain regional events, and global dust storms can affect large areas. If a mission relies heavily on solar power, it must have storage and backup capacity sufficient to maintain life support and heating through low generation intervals. If storage is insufficient, the crew must reduce power use. In a habitat, reduced power often means reduced heating and reduced ventilation. These reductions can cascade into system stress. The crew can survive short reductions. Long reductions can damage equipment and threaten life support. All of these environmental constraints connect back to the idea of return. Return capability is not only a rocket sitting on a pad, it is a sequence of operations that must be sustained until the correct window. That sequence includes maintenance, power, water recycling, oxygen control, and medical readiness. A base that is barely holding on may keep the crew alive but may not keep them capable of launching and surviving a return flight. A degraded crew health state combined with a degraded system state can make return physically impossible even if a vehicle exists, because the return is another long interplanetary exposure. The Martian environment also complicates the preservation of hardware needed for return. The ascent vehicle and its systems must remain within thermal limits. Tanks must remain sealed, valves must not seize, dust must not foul critical interfaces. If the ascent vehicle uses cryogenic propellants, long-term storage is difficult because cryogenic fluids boil off unless actively cooled or insulated exceptionally well. This pushes mission designs toward storable propellants or toward producing propellants closer to departure. Either approach increases dependence on surface systems. The environment therefore shapes propellant choices, and propellant choices shape the likelihood of return. In this region, the realism is steady. Mars is cold, dry, and thin-aired. It offers no breathable atmosphere, little pressure, and little protection. Dust is persistent and abrasive. Thermal cycling stresses materials. Habitats and suits must function as life support machines continuously. Power is required for heating, recycling, and communications. Failures accumulate because resupply is slow. These facts mean that a long surface stay, often required by orbital windows, is not simply a waiting period. It is a prolonged test of system reliability and human health. If the test is failed in certain ways, the crew may survive but lose the ability to depart. turning the first Mars mission into a stay without return. From this daily survival layer, the inward path moves toward a less visible but equally persistent hazard that accumulates with time and distance radiation exposure beyond Earth's shielding, across the cruise phase and the long surface stay. Beyond Earth, radiation becomes an environment rather than an event. Earth's magnetic field and thick atmosphere reduce exposure on the surface and in low orbit. A Mars mission leaves most of that protection behind. During the cruise, the spacecraft travels through interplanetary space where energetic particles can penetrate habitats and human tissue. On the surface of Mars, the thin atmosphere provides only modest shielding, and the planet lacks a strong global magnetic field to deflect charged particles. Radiation exposure therefore accumulates across months of travel and months or years of surface stay. This accumulation is a quiet reason a first crew may never return. Even when no dramatic storm occurs, the long-term dose can rise toward limits that constrain mission duration and complicate decisions about waiting for a return window. Two broad sources dominate the discussion. Galactic cosmic rays are high-energy particles that arrive from outside the solar system. They are mostly protons and heavier nuclei accelerated by distant astrophysical processes. They are difficult to stop because of their high energy. When they strike spacecraft materials or human tissue, they can produce secondary particles that spread energy through the body. The dose from cosmic rays is relatively steady, varying with the solar cycle, but it is always present. Solar energetic particles are bursts associated with solar flares and coronal mass ejections. They can arrive in short intervals and can raise radiation levels sharply. These events are more sporadic, and their intensity can vary widely. They can be dangerous because high dose can arrive quickly, and protection depends on sheltering in shielded areas. The cruise to Mars is a radiation exposure interval because the spacecraft is in free space. There is no planetary atmosphere above. Shielding must be provided by the spacecraft itself. Shielding works by absorbing energy and by reducing the number of particles that reach the body. Dense materials can block some particles, but dense materials can also produce secondary radiation when hit by high-energy cosmic rays. Hydrogen-rich materials, such as water and certain plastics, can be more effective at slowing some particle types while producing fewer harmful secondaries, yet no practical shield can stop all cosmic rays at the mass limits of a spacecraft. Therefore, a Mars mission accepts that cosmic ray exposure will occur and aims to reduce it and manage it. Travel time then becomes critical. The longer the cruise, the more exposure accumulates. This links radiation to the orbital timing discussed earlier. A trajectory that increases travel time can increase cumulative dose. Solar energetic particle events represent a different kind of risk. They can deliver high dose rates over hours to days. Protection is achieved by sheltering in a storm shelter, a part of the spacecraft with extra shielding. Storm shelter design can use stored water, food supplies, and equipment arranged around a small volume to increase shielding mass where it is most needed. The shelter must be accessible quickly, because warning time can be limited. Space weather forecasting can provide some notice, but forecasts are imperfect. A mission must therefore maintain readiness to shelter and must ensure that life support can be sustained in that shelter for the duration of an event. This is another reliability constraint. The shelter is not only a safe room, it is a life support node that must work when the rest of the habitat may be placed into a reduced state. On Mars, radiation conditions improve slightly compared with deep space because the planet blocks half the sky, and the thin atmosphere provides some shielding. Yet the improvement is limited. The Martian atmosphere is too thin to provide the protection Earth provides. It reduces some particle energies and stops some secondaries. but many cosmic rays still reach the surface. Mars also lacks a global magnetic field that could deflect charged particles over the whole planet. Local crustal magnetic fields exist in patches, but they do not create a planet-wide shield. Therefore, surface exposure remains substantial. Over a long stay, this exposure can become a dominant contribution to total mission dose. Shielding on the surface can be improved by using local materials. Regolith, the layer of dust and broken rock on the surface, can be piled over habitats. Habitats can be placed in natural depressions or behind berms. Inflatable modules can be buried. These strategies can reduce exposure, but they require equipment and time. Bulldozers and excavators are heavy and complex to land and maintain. Robotic construction may help, but it adds system complexity. Early missions may use a combination of modest shielding built into habitat walls and additional shielding created by placing supplies and water around living areas. This can reduce dose, but may not reduce it to near-Earth levels. Therefore, the mission must still manage cumulative exposure as a key constraint. Radiation is not only a cancer risk in long-term statistical terms, it can have more immediate effects on tissue and on nervous system function at high doses, and it can degrade electronic systems and sensors. Crew health risk is managed by limiting total dose. If a mission is delayed and the crew must stay longer than planned, total dose increases. If a return window is missed, additional months or years on the surface can push dose beyond planned limits. The mission then faces a harsh trade-off. Leaving earlier might not be possible due to orbital geometry or fuel readiness. Staying longer increases dose. In such a situation, the crew may remain alive and functional, but the risk of long-term health damage rises. For early crews, where mission design margins are narrow, these dose limits can be part of why a plan shifts from return to extended stay. The radiation environment also interacts with medical care. A weakened immune response from stress and altered physiology can increase vulnerability to infection. Some evidence from spaceflight indicates that immune function can change in microgravity and under stress. Mars gravity is not microgravity, but the mission includes a microgravity cruise and a high-stress environment. Radiation can also contribute to cellular damage. This does not mean immediate illness in most cases. It means an accumulation of risk and a reduced margin against other health problems. In an environment where evacuation is not possible, reduced margin matters. Radiation affects psychological factors as well. The awareness of exposure can add to stress. Sheltering during solar events compresses crew into small spaces for hours or days. This can disrupt sleep and routine. It can also interrupt critical operations, such as external repairs or surface activities. If a solar event occurs during a time when the base is already under power stress or equipment failure, the need to shelter can make repair harder. This is another way in which separate risks can compound rather than remain isolated. Even in a quiet solar period, cosmic rays continue. The dose accumulates gradually, day after day. The only effective way to reduce this accumulation is to reduce time or increase shielding, and both are constrained. Reducing time is constrained by orbital windows and mission design. Increasing shielding is constrained by mass and by construction capability. Therefore, radiation becomes a planning limit. It shapes acceptable mission duration. It shapes how long a crew can safely wait for a return opportunity. It also shapes whether a rescue mission is meaningful, because sending a new crew to deliver supplies would expose that crew as well, and the timing would still be slow. Uncertainty remains in the exact biological impact of long-duration exposure beyond Earth's protective field. Data from human spaceflight comes primarily from low Earth orbit missions. where Earth's magnetosphere reduces exposure. Deep space exposure for humans is limited in modern data. Mars surface exposure has been measured by robotic instruments, but translating those measurements into long-term human outcomes involves models and assumptions. Observations indicate that radiation is a real and significant hazard, and it remains uncertain exactly how the risk translates into specific health outcomes for a given crew. This uncertainty does not reduce the hazard, it increases the need for conservative planning, because unknowns are managed by margin. In the context of return, radiation hazard interacts with time geometry. A mission that relies on waiting for windows must ensure the crew can tolerate the total dose of the entire timeline. If unexpected delays extend the mission, radiation can become one of the hard reasons the mission cannot simply wait indefinitely for the next chance. The crew may remain alive, but returning may no longer be acceptable or possible if the exposure has already reached limits, and if the return trip itself adds more dose. In a worse case, the mission could become a decision between staying on Mars with sheltering and reduced travel exposure versus risking a return flight that adds significant additional dose when the crew is already near limits. The existence of this trade-off is a realistic part of early Mars mission planning. This region therefore adds a quiet accumulation to the story. Radiation is present in crews and on the surface. Galactic cosmic rays provide a steady background that is difficult to shield fully. Solar energetic particles add intermittent spikes that require shelter. Mars provides limited shielding and no global magnetic field. Shielding strategies exist but are constrained. Exposure accumulates over months and years, linking directly to delays and missed windows. In this way, radiation becomes not a single dramatic threat, but a persistent limit that can turn an extended stay into a mission that cannot safely proceed to a return, even if the crew remains technically capable. From this accumulation layer, the inward path moves to the closed-loop systems that sustain life day after day, where small inefficiencies and failures can compound over long time, determining whether a crew has enough breathable air, clean water, and stable conditions to survive until any return becomes feasible. A Mars habitat survives by closing loops. Air must be cleaned and refreshed, water must be recovered and reused, waste must be managed, food must be stored and rationed, and in some designs, partly grown. These loops not optional because the cost of delivering large masses from Earth is immense, and because resupply is slow. In near-Earth missions, life support has redundancy and the possibility of rapid cargo flights. On Mars, the loop must remain stable across months of isolation, with only the supplies and spares that were brought in advance. This is a quiet reason a first crew may never return. Return depends on endurance. Endurance depends on closed-loop performance. Small failures that would be manageable on Earth can become mission-ending when they persist for a long time and cannot be replaced. Air management begins with oxygen supply and carbon dioxide removal. Humans consume oxygen and produce carbon dioxide continuously. A habitat must replenish oxygen and prevent carbon dioxide from building to harmful levels. Oxygen can be stored in tanks, generated from water by electrolysis, or produced through chemical processes that split carbon dioxide. Each method has constraints. Stored oxygen provides simplicity but is finite. Electrolysis requires water and power. Carbon dioxide processing requires equipment, power, and reliable catalysts or reaction chambers. The most realistic approach uses a combination storage for contingency, plus generation for long-term sustainability. The problem is reliability. A generator that works for a week is not enough. It must work for many months. It must work through power fluctuations. It must work with dust infiltration and thermal cycling. If it fails and cannot be repaired, stored reserves become the only oxygen source, and the clock starts. Carbon dioxide removal systems also have finite capacity. Many designs use sorbents, materials that absorb carbon dioxide and then release it when heated or depressurized. These systems can be regenerative, meaning the sorbent is reused, but the mechanism requires valves, heaters, pumps, and sensors. Each component can fail, filters can clog, fans can wear, a leak in a duct can reduce efficiency. Over months, these small degradations can matter. If carbon dioxide removal becomes less effective, carbon dioxide can rise to levels that impair cognition, sleep, and health. The crew may compensate by reducing activity, because activity increases carbon dioxide production. Reduced activity can then affect fitness and ability to perform external work. In this way, air loop problems can cascade into operational limitations. Water management is similarly central. Water is used for drinking, food preparation, hygiene, and sometimes for plant growth. It is also used in certain cooling systems. A Mars base can recycle water through condensation capture, filtration, and chemical treatment. Urine and wastewater can be processed to recover water. These systems are complex and must be reliable. They involve membranes, pumps, heaters, and sensors. They also involve chemical additives and microbial control. If microbial growth occurs in water lines, it can clog filters and create health risks. If a membrane fails, recovery efficiency drops. If a pump fails, the system can stop. On Earth, a failed pump can be replaced quickly. On Mars, replacement depends on whether the spare exists and whether the crew can install it. If a critical component fails and no spare is available, the crew must improvise. Improvisation in life support is possible within limits, but each improvised solution can reduce efficiency and increase risk. Leakage is a persistent enemy of closed-loop design. A tiny leak in a water line can lose liters over weeks. A slow leak in a habitat system can go unnoticed until a reservoir is lower than expected. On Earth, a leak is an inconvenience. On Mars, it is a loss of mass that cannot be replaced quickly. This is why Mars mission designs often treat water as both consumable and shield. Water stored around sleeping quarters can reduce radiation. If water is lost, shielding can decrease as well. The loss therefore affects both hydration and radiation protection. The coupling of resources is a feature of realistic missions. It can improve efficiency when all is well, and it can create cascading vulnerability when something fails. Food is the most visible loop and also one of the hardest to close fully. Stored food can sustain a crew for a planned mission duration, but it adds mass and volume. Food must also remain safe and palatable over long storage. Vitamins can degrade, fats can oxidize, packaging can fail. Thermal cycling and radiation can alter some food items over time. Growing food on Mars is possible in controlled environments, but it is not a simple replacement for stored supplies in early missions. Plants require light, water, nutrients, and controlled temperature. They require careful microbial management. They require time, because crops have growth cycles. If a crop system fails, it cannot be restarted instantly. It can take months to recover yield. Therefore, early missions are likely to rely primarily on stored food, with modest supplemental growth for freshness and psychological benefit, rather than for full caloric independence. The limitations of food loops matter for return because extended stays consume stores. If a mission is delayed and the crew must remain on Mars longer than planned, food becomes a hard limit. Rationing can extend time, but rationing reduces health and performance. A crew underfed for months will lose muscle, lose cognitive sharpness, and become more vulnerable to illness. This makes return, which requires demanding physical tasks and then a stressful interplanetary flight, more difficult. Therefore, a prolonged delay can transform food from a comfortable margin into a critical countdown. The crew may remain alive but less capable of executing a safe departure. Waste management ties into air and water. Waste contains water and nutrients. Waste also contains microbes. A habitat must manage waste to prevent contamination and to keep air quality stable. Odors and trace chemicals can build in a closed environment. Chemical scrubbers and filters must control these. If filters saturate and cannot be regenerated, air quality declines. If waste storage is compromised, microbial growth can increase. In a sealed habitat, this can affect health. The crew can clean and sterilize, but cleaning consumes water and supplies and takes time. The need to spend time on maintenance and hygiene increases as systems degrade. Power is the hidden driver of all loops. Air processing requires fans and heaters. Water recycling requires pumps and heaters. Lighting for crops requires power. Temperature control requires power for heating and ventilation. If power dips, systems may be shut down or run at reduced capacity. Reduced capacity can cause carbon dioxide to rise or water recovery to fall. These changes can then require compensations that consume more power or more stored resources. Power therefore links directly to life support stability. In a dust storm, solar power may fall. If storage is limited, the crew must triage which systems run at full capacity. These choices can affect health over time. A mission that relies on power margins can become vulnerable when those margins are reduced by dust, equipment degradation, or unexpected consumption. Closed-loop systems also require maintenance, and maintenance requires spares. Filters must be replaced, seals must be changed, pumps must be swapped, sensors must be calibrated. On Mars, the crew is the maintenance team. This requires time, training, and physical ability. If the crew is already stressed by radiation exposure, sleep disruption, or medical issues, maintenance quality can suffer. A small mistake can create a leak or a contamination event. In this way, life support becomes a dynamic system involving both machines and human attention. The first crew will operate at the edge of experience, because no human habitat has been maintained on Mars before. The system may be designed well, but unknown interactions will appear. Managing those unknowns consumes margin. Uncertainty exists in how well closed-loop systems can perform over the full duration of a Mars mission without resupply. Observations from space stations show that life support can be sustained for long periods, but those systems benefit from periodic resupply and repair. A Mars mission must achieve a higher standard of autonomy and reliability. It remains uncertain which failures will be most common and which components will be most vulnerable under Mars dust and thermal conditions. This uncertainty is not a reason for despair. It is a reason for conservative design and redundant architecture. Yet redundancy adds mass. Mass increases landing difficulty. The same loops appear again. In this region, the logic stays steady. A Mars mission must close loops for air and water and manage food over long time. Each loop depends on complex machinery and constant power. Small failures accumulate because resupply is slow. Maintenance demands attention and spares. Extended stays consume food and supplies. If a return window is missed, the loops must remain stable for much longer than planned, and the margin can vanish. A crew can be stranded not by a sudden catastrophe, but by a gradual decline in loop performance that makes continued survival possible, but makes departure risky or impossible. From this life support loop layer, the inward path moves to the infrastructure that keeps the loops running: power generation, maintenance capacity, and spare part logistics, where dust and distance make even basic engineering into a long-duration test. A Mars base lives or dies by its ability to keep machines running. Power, maintenance, and spare parts are not separate concerns. They are a single fabric of reliability. Life support needs electricity. Heat needs electricity. Communications need electricity. Water recycling needs electricity. If power declines, every other system becomes harder to sustain. If a key component fails and cannot be replaced, power may be available but unusable for essential loops. If spare parts exist but tools and procedures are inadequate, the spares remain inert. The first humans on Mars may never return, not because a return rocket cannot be designed, but because a base cannot remain reliably maintained long enough to reach a return window and still be capable of departure. Power on Mars can be generated primarily through sunlight or through nuclear sources. Each has strengths and weaknesses. Solar power is mature and scalable, but Mars sunlight is weaker than Earth sunlight, and dust is persistent. Dust settles on panels and reduces output. Regional dust storms can reduce sunlight for days or weeks, and global dust storms can reduce it further across large areas. Even when storms are not present, a steady accumulation of dust can degrade panel performance. Robotic dust clearing systems can help, but they add complexity and require their own power and maintenance. A crew can clean panels manually, but that requires outside work in suits, which consumes time, oxygen, and risk. The base therefore cannot treat solar arrays as passive. It must treat them as surfaces that require constant attention. Nuclear power offers a different balance. A fission system can provide steady electricity regardless of dust or season. It can reduce dependence on large panel fields and large batteries. Yet nuclear systems add mass and complexity. They require thermal management. They must be protected and handled safely. They may be politically and programmatically difficult to deploy at large scale. They also still require maintenance and spares. A system designed to run unattended for years on Earth may still face unexpected challenges on Mars, such as dust intrusion into external cooling structures or temperature cycling affecting seals and materials. In a realistic mission, the choice is not between perfect solar and perfect nuclear. It is between different failure modes. Many architectures therefore consider hybrid systems, using nuclear for baseline power and solar for supplemental capacity, or using solar with large storage and carefully planned dust mitigation. Each choice influences how fragile the base becomes under extended stays. Energy storage is a crucial link. Solar generation varies with day and night and with dust. Batteries or other storage systems must cover darkness and low generation intervals. Batteries degrade over time. Their capacity falls with cycles and with temperature stress. Mars nights are cold. Batteries must be kept within temperature limits to preserve health and deliver power safely. Thermal control for batteries consumes power, creating another loop. If a battery bank loses capacity, the base may survive during normal days but become vulnerable during storms or during higher demand periods. The crew then must ration power. Rationing can mean reduced heating, reduced air circulation, reduced water processing, and reduced communications. These reductions can be survivable briefly but harmful over long time. Power distribution is also a reliability challenge. Cables, connectors, and power electronics must operate in cold, dusty conditions. Connectors can corrode or become clogged with dust. Electrical arcs are possible in certain fault states. Power management software can fail. A base must be able to isolate faults and reroute power. Redundancy is required not only in generation but in distribution. If a single point of failure exists in a main power bus, a small fault can shut down large portions of the base. Designing and testing such distribution under Martian conditions is difficult because the exact combination of dust, thermal cycling, and operational wear is hard to reproduce on Earth at full scale. Maintenance is the human response to these engineering realities. On Mars, the crew becomes the maintenance workforce. This demands time, strength, and sustained cognitive performance. The crew must inspect seals, replace filters, repair pumps, recalibrate sensors, and respond to faults in power systems. They must do this while also performing scientific tasks, building infrastructure, and managing their own health. Maintenance load can rise over time as systems age. The first months may be smooth, and then wear accumulates. Dust abrades joints, lubricants thicken in cold, plastics and elastomers harden under radiation and temperature cycling. Fans and motors wear, valves stick. A mission that is delayed beyond its planned duration will face a higher rate of maintenance as systems pass their design life. Spare parts are the only buffer against this aging. A Mars base must carry a spare inventory for likely failure modes, yet predicting failure modes is hard even for mature systems. Some parts fail rarely on Earth because they are maintained regularly or replaced during scheduled service. On Mars, scheduled service depends on spares and time. A spare inventory can cover common items, but it cannot cover every possible failure at the component level without becoming enormous. Mass limits prevent carrying duplicates of every system. Therefore, the base must choose a strategy, carry spares for high likelihood failures, carry tools for fabrication and repair, and rely on modular design so that components can be swapped rather than repaired in place. Fabrication capability becomes an attractive supplement. A base can carry a manufacturing system such as a three-dimensional printer for certain materials, plus machining tools for simple parts. This can produce brackets, housings, and certain plastic components. It can also produce tools and adapters. Yet fabrication has limits. It cannot easily produce high-precision valves, electronic chips, complex membranes, or chemical catalysts. It cannot produce replacement seals for all situations unless appropriate materials are present. It cannot produce high-pressure tanks. Therefore, fabrication is a partial solution. It can reduce vulnerability to simple mechanical breakage, but it cannot eliminate the need for critical spares. Tools and procedures also matter. A crew can have the right spare and still fail to install it safely if procedures are inadequate, or if the repair requires fine control in bulky gloves or in cramped spaces. Some maintenance tasks will occur inside the habitat where dexterity is good. Others will occur outside, where suit limitations reduce dexterity and increase fatigue. External repairs can be especially difficult because dust can enter open equipment and because visibility can be reduced. A crew may choose to postpone external repairs to avoid risk, but postponement can allow a problem to worsen. This is another quiet way in which risk accumulates. The safest short-term choice can increase long-term risk. The base's mechanical and electrical systems must also withstand the Martian environment for extended periods without human intervention during some intervals. During storms or during periods of fatigue or medical events, the crew may reduce external activity. The base must be able to maintain itself in a stable mode. Automated diagnostics and self-protection are essential. Yet automation adds software complexity, and software can have errors. A safe mode that protects one system can harm another by shutting down a needed subsystem. Testing all interactions is difficult. Therefore, Early missions will likely operate with conservative margins and frequent checks, which increases crew workload and stress. The workload itself becomes a risk factor because it consumes time and attention that might otherwise be used for rest and recovery. Logistics extends beyond spares to consumables, filters, chemical scrubbers, lubricants, and certain pharmaceuticals are consumables. Their supplies are finite. If an extended stay occurs, consumables can become limiting even if major hardware remains intact. A base can reduce consumption by operating at lower performance or by reusing items beyond their intended life, but this can increase failure probability. Again, small decisions become long-term trade-offs. The possibility of non-return becomes more realistic when power and maintenance are considered together with launch windows. A crew might land with a return plan that assumes a certain level of system health at a future departure date. If power output declines due to dust and battery degradation, and if maintenance demands rise, the crew may face a choice between using time and resources to maintain return hardware or using them to maintain life support. In a severe case, the crew may preserve survival at the cost of return readiness. The return vehicle may remain physically present but not properly fueled, not properly checked, or not properly maintained for launch. When the return window arrives, the crew may be alive but not in a condition to depart safely, either because systems are too degraded or because health has declined. This region also highlights why early Mars missions are likely to be conservative and why they may still face one-way risk. Reliability at scale on Mars has not been demonstrated. Power systems have been deployed robotically, but not at the scale of a human base. Life support has been maintained in orbit with resupply, not in a dusty surface environment with years of isolation. The maintenance and spare part burden for such a system is uncertain. This uncertainty is itself a risk. A mission can plan for known failures, but unknown failure patterns can erode spares and time faster than expected. In this calm framing, power, maintenance, and spares become the base's heartbeat. Solar arrays degrade under dust. Batteries degrade under cycles and cold. Nuclear options bring different complexities. Distribution systems must isolate faults. The crew must maintain everything while living inside it. Spare inventories are finite and cannot cover all failures. Fabrication helps but cannot replace critical components. Consumables run down. As time extends due to missed windows or delays, these pressures increase. Return then becomes not a single event but an outcome that depends on system health at the exact moment of departure. If the base can keep itself alive but cannot keep itself capable, the first humans on Mars may remain, not by intention, but by the slow arithmetic of wear and logistics. From this infrastructure layer, the inward path moves to the medical reality of a Mars mission, where the absence of evacuation and the limits of treatment make some health events irreversible in their consequences for return, even if the crew survives the initial crisis. Medical care on Mars is shaped by one missing option: evacuation. On Earth, severe illness or injury is met with rapid transport to advanced care. In low Earth orbit, evacuation is still possible within hours. On Mars, evacuation is not immediate, and often not possible at all within the timescale of acute medical emergencies. The distance imposes travel time, and the launch window imposes waiting time. A crew can survive a medical event and still lose the ability to return, because recovery may not align with the departure schedule, and because the return journey itself is physically demanding. This is a central realistic reason early crews may never return. It is not about drama. It is about the limits of medicine and the limits of time. Medical risk begins in transit. The cruise to Mars is months in a closed habitat, microgravity, confined space, altered sleep cycles, and radiation exposure all affect physiology. Microgravity causes fluid shifts toward the head and changes in cardiovascular function. Muscles and bones can weaken without constant exercise. Vision changes can occur in some individuals due to fluid and pressure changes. Immune function can shift under stress and altered environments. None of these effects guarantee severe illness, but they reduce margin. A crew arrives at Mars after a long period of physiological adaptation, not at baseline Earth condition. This matters because landing, surface operations, and eventual return all demand physical resilience. Once on Mars, gravity is partial. It is not zero, but it is lower than Earth's. This can help restore some muscle loading compared with microgravity. Yet it does not erase the need for exercise and countermeasures. The crew remains in a confined habitat, exposed to dust and to the psychological pressures of isolation. Nutrition may be less varied. Sleep may be disrupted by scheduled demands and by the slightly longer Martian day. These factors can affect recovery from minor illness and can increase the chance that small problems become larger ones. The medical system on Mars must therefore be prepared for a wide range of conditions. Trauma from falls, cuts, burns, and equipment accidents is possible. External work in suits carries risk because suits limit dexterity and visibility, and because fatigue increases with exertion. A simple fall can produce fractures. A fracture on Earth is treatable with immobilization and surgery when needed. On Mars, surgery is limited. Sterile conditions are harder to maintain. Blood storage and transfusion are constrained. Imaging equipment is limited. Even when basic surgery is possible, complication management is difficult without an intensive care unit. Therefore, certain injuries that are survivable on Earth can become disabling on Mars, and disability can prevent return because return requires demanding physical tasks and exposure to high acceleration events during launch and landing phases. Infection is another risk. The habitat is closed and microbes live on and within humans. Small infections can arise from skin cuts, dental problems, or respiratory issues. Antibiotics can treat many infections, but antibiotic choice depends on diagnosis and sensitivity, and not all medications can be stocked in large quantity or kept stable for years. Medication stability is a quiet constraint. Many pharmaceuticals degrade over time, especially under temperature cycling and radiation exposure. Packaging can protect drugs, but long storage in space environments remains challenging. If a key medication loses potency, treatment options narrow. This is a realistic reason why long delays can change outcomes. A mission planned for a certain duration can stock medications accordingly. An extended stay can push supplies beyond their safe storage life. Chronic conditions can also emerge. Kidney stones are a concern in spaceflight because of fluid shifts, changes in calcium metabolism, and dehydration risk. A kidney stone can be acutely painful and can obstruct urine flow, leading to infection or kidney damage. Treatment on Earth can involve imaging, pain control, and procedures. On Mars, pain control supplies are limited, imaging may be limited, and procedures may be difficult. A severe case can become mission-ending in a practical sense, disabling a crew member and consuming resources. Cardiovascular events are less likely in carefully selected astronauts, yet risk is not zero, especially as missions extend and crews age. A heart rhythm disturbance or a clot can be fatal without advanced intervention. The mission must manage this by selection, screening, and preventive measures, but it cannot eliminate risk completely. Dental problems are a known challenge in remote expeditions. A cracked tooth, abscess, or severe decay can become a major health issue. Dental repair requires tools, anesthetics, and skill. A crewed mission can train a medical officer for dental emergencies, but complex cases remain difficult. Pain and infection can affect sleep and performance. Again, these effects can reduce the crew's ability to maintain systems and to prepare for return. A crew may remain alive but less capable. Mental health is often discussed separately, but it has medical consequences. Prolonged stress, isolation, and conflict can affect immune function and sleep. Sleep disruption affects cognition, mood, and decision-making. Depression and anxiety can reduce motivation and performance. In a base that depends on constant maintenance and careful procedure, reduced performance can increase accident risk. Mental health support from Earth exists but is delayed. The crew must rely on internal routines, social stability, and self-regulation. Medical management may include counseling and, in some cases, medication. Medication again depends on stability and supply. The absence of evacuation changes triage. On Earth, triage includes deciding who should be transported to advanced care and who can be treated locally. On Mars, advanced care is not available. Triage becomes a decision about resource allocation and risk management within the base. It may involve long-term care for a disabled crew member. Long-term care consumes time, supplies, and attention. The crew must continue operating the base while also providing care. This can strain the mission. It can also reduce redundancy, because each crew member often has specialized skills. Losing one crew member's capacity can create gaps in maintenance, operations, or medical care. These gaps can increase risk of system failures, further endangering return capability. The return journey itself is medically demanding. Leaving Mars requires ascent, which involves acceleration and a high-stress launch environment. A crew member who is recovering from injury or illness may not tolerate launch forces well. The interplanetary return involves months in a confined habitat with radiation exposure and limited medical support. A crew member with a compromised immune system, reduced mobility, or ongoing medical needs may not be able to complete the return safely. Therefore, even if a return vehicle is technically available, a medical condition can render return infeasible. A crew may choose to stay rather than attempt a return that would likely be fatal. This is a realistic pathway to non-return that does not require catastrophic failure of rockets or life support. Medical planning can mitigate some of these risks through redundancy and training. Multiple crew members can be trained in medical procedures. The base can carry ultrasound imaging, basic laboratory capability, and a set of surgical tools. It can carry medications for common conditions and emergency interventions. It can carry oxygen and fluid resuscitation supplies. Yet every medical capability adds mass and complexity, and not all capabilities can be carried. The mission must choose what is most likely and most treatable. Rare but severe events remain a gap. The mission therefore relies on selection and prevention as much as on treatment. Uncertainty remains in how the combined stresses of deep space radiation, partial gravity, confinement, and long duration will affect human health over a multi-year Mars mission. Observations from low Earth orbit provide partial guidance, but Mars missions include longer exposure in different environments. It remains uncertain how often certain conditions will occur and how severe they will be. This uncertainty again encourages conservative planning. It also suggests that early missions may accept higher risk or restrict mission duration tightly. Yet orbital windows and base logistics can force longer duration than planned. This tension is central to the realistic argument. A mission can plan for one timeline and be forced into a longer one by delays. Medical supplies and resilience may not scale easily with forced extension. In this region, the conclusion is steady. Medical care on Mars is limited by the lack of evacuation and by the constraints of equipment, supplies, and time. Injuries and infections that are manageable on Earth can become disabling. Medication stability and supply can become limiting in extended stays. Chronic conditions can emerge. Mental health can affect operational safety. A single incapacitating medical event can reduce crew capability and strain base maintenance. Return requires physical resilience, and some conditions can make return too risky even if hardware exists. These facts form a realistic pathway by which the first humans on Mars may survive yet remain unable to return. From this medical layer, the inward path moves toward human factors and psychology not as a separate soft topic, but as an operational system that affects safety, maintenance quality, decision-making, and the long-term ability to sustain a mission until return is possible. A Mars mission is sustained by attention. Attention is shaped by sleep, mood, and the slow wear of isolation. Human factors are sometimes treated as secondary compared with the rockets and life support. Yet, in a long mission, with delayed communication and high maintenance demands, the human element becomes part of the engineering. The first humans on Mars may never return not only because hardware can fail, but because the people required to keep hardware functioning can become fatigued, stressed, and less effective over time. This is not a moral judgment. It is a predictable feature of prolonged confinement under high consequence, where small errors have large costs. Isolation begins before arrival. The cruise is months inside a limited volume. The crew sees the same walls, breathes recycled air, and lives under artificial lighting and schedule. The outside view is space and distance, with no weather, no vegetation, and no everyday variation. The crew shares work and rest with the same small group continuously. Privacy is limited. Noise from fans and pumps is constant. Even when everything is functioning, the environment is not neutral. It is a steady sensory constraint. Over time, such constraints can change sleep quality, irritability, and cognitive performance. A Mars mission relies on the crew maintaining performance while living inside this constraint for months, then continuing under different but still constrained conditions on the surface. Sleep is one of the most important factors. Sleep disruption affects attention, memory, and emotional regulation. In spaceflight, sleep can be disrupted by noise, by stress, by schedule demands, and by changes in light exposure. On Mars, the day is slightly longer than on Earth, and the difference can complicate circadian alignment. A crew can adjust with disciplined scheduling and lighting control, but adaptation varies among individuals. If sleep debt accumulates, the crew becomes more prone to mistakes. Mistakes in a Mars base can mean incorrect valve settings, missed warning signs in telemetry, improper maintenance steps, or poor judgment in deciding whether to go outside during marginal conditions. A single error can be corrected when resources and time are plentiful. In a constrained base, repeated small errors can degrade systems and consume spares. Confinement also changes social dynamics. A small crew must cooperate continuously. Differences in personality, work style, and stress response become important. Conflict can arise over workload, risk tolerance, and decision authority. Conflict can be managed, but management requires communication, trust, and time. If conflict becomes chronic, it consumes attention and reduces the efficiency of maintenance and planning. It can also lead to communication breakdown, where critical information is withheld or not shared clearly. In a high-reliability environment, clear communication is itself a safety system. Therefore, interpersonal friction can be a technical risk factor. Delayed communication with Earth amplifies these dynamics. When ground support is immediate, it can provide not only technical advice but also emotional buffering and external perspective. On Mars, messages arrive late. Real-time coaching is not possible. This means the crew must solve conflicts internally and must make high-stakes decisions without immediate external arbitration. Earth-based teams can advise and can provide structured psychological support, but the delay changes its effectiveness. The crew can feel that Earth does not fully share the mission's immediate reality. This can deepen the sense of being alone, which can affect mood and decision-making. The surface environment adds additional stressors. External activity requires suits and careful procedures. Every excursion carries risk. The need to suit up and depressurize airlocks creates friction in daily work. The crew must plan tasks carefully, because a simple forgotten tool can mean another time-consuming excursion. The cold and dust make external work uncomfortable. The thin air offers no forgiving margin. The knowledge that the outside environment is lethal without protection can intensify stress in ways that are subtle but persistent. This stress can be managed, but management is an ongoing task. Cognitive load is also high. A Mars mission requires constant monitoring of life support, power systems, water recycling, and communications. It requires planning for repairs and rationing. It requires scientific work, because missions are often justified partly by science. And scientific work has its own complex procedures. It requires medical monitoring and exercise routines. It requires training refreshers and safety drills. The crew must manage this workload while also maintaining emotional stability and rest. Over time, the workload can increase as systems age and maintenance demands rise. If a delay forces an extended stay, the workload can become chronic, leaving little recovery time. Chronic workload without adequate rest increases error probability. Risk perception changes over time as well. In the early phase, the crew may be vigilant and cautious. Over months, routine can breed complacency, especially if systems have been stable. Complacency can lead to skipping steps, rushing checks, or assuming alarms are false. The opposite pattern is also possible. Chronic stress can lead to hypervigilance and fatigue, where every alarm feels like a crisis. This can lead to decision paralysis or to hurried actions. Both extremes are dangerous in a high-consequence system. Maintaining a balanced risk posture is an ongoing effort, and it depends on leadership, crew culture, and well-designed procedures that reduce unnecessary burden. Psychological health is also tied to meaning and monotony. A crew on Mars may be motivated by mission purpose, exploration, and achievement. That purpose can sustain morale, yet purpose does not remove daily monotony and frustration. A base that requires constant maintenance can feel like a life spent inside machinery. If the mission goal is delayed, such as if scientific exploration is curtailed by power shortages or medical events, morale can fall. If a return date becomes uncertain due to a missed window or hardware failure, the psychological weight can increase sharply. Uncertainty can be more stressful than a known long duration, because it removes the ability to plan mentally for an end. In such a scenario, the crew may become more prone to depression and conflict, which then feeds back into operational risk. The environment also influences sensory and social support. On Earth, people rely on contact with family and broader communities. On Mars, contact exists but is delayed and scheduled. The content of communication must be managed to avoid overwhelming the crew with Earthside problems they cannot affect. the crew's sense of connection can depend on messages, recordings, and planned exchanges. These can help, but they are not the same as presence. The crew must also cope with the knowledge that family and friends on Earth continue life without them, and that important events at home occur while the crew is distant and unable to respond. This can create sadness and distraction. Distraction can affect safety in a place where attention matters. Operational psychology also includes team structure. Roles must be clear. Decision authority must be defined. Emergency protocols must be rehearsed. When a fault occurs, the crew must shift into an emergency mode efficiently, with each person knowing tasks. Confusion in roles can waste time and create conflicting actions. On Mars, with delayed Earth input, role clarity is even more important. The crew must be able to operate as an independent unit. This requires training and ongoing practice. Yet practice consumes time and energy. If time becomes scarce due to maintenance demands, practice may be reduced, increasing risk during real emergencies. This is another way extended stays can erode safety. Human factors also affect health directly through behavior. Reduced motivation can reduce exercise, accelerating deconditioning. Stress can alter appetite and sleep. Conflict can lead to social withdrawal. Social withdrawal can reduce communication about problems, including medical symptoms and technical concerns, in a high-reliability setting. Early reporting is essential. Therefore, psychological decline can hide technical and medical issues until they become severe. This increases the chance that a manageable problem becomes unmanageable. The link to non-return becomes clear through these feedbacks. A crew must maintain systems reliably until the return window. Systems age and require maintenance. Maintenance demands attention. Attention depends on sleep and mood. Sleep and mood are challenged by isolation and uncertainty. If performance declines, errors increase. Errors consume spares and time. Consumed spares and time reduce margin. Reduced margin increases stress. Stress further degrades sleep and mood. This is a realistic loop. It does not require a dramatic event. It requires only a prolonged period of strain and uncertainty, which is plausible in early Mars missions. Mitigation exists. Crew selection focuses on psychological resilience and teamwork. Training includes conflict management and stress coping. Habitats can be designed for better privacy and noise control. Lighting can support circadian rhythm. Work schedules can include protected rest time. Communication protocols can maintain connection. Recreation and meaningful work can support morale. These are real tools, but they do not eliminate the underlying constraints. Isolation and delay remain. Delay. The environment remains hostile. The mission remains long. The best mitigations reduce risk but cannot remove it. This region therefore treats human factors as an operational system. Sleep, stress, and social dynamics affect attention and decision-making. Decision-making affects maintenance quality. Maintenance quality affects base reliability. Base reliability affects return readiness. When timelines extend due to missed windows or system failures, the human system is strained longer than planned. Under severe strain, a crew may remain alive but less capable of executing a safe launch and return. In that sense, human factors become one more realistic pathway toward non-return. From this inner human layer, the inward path moves back to a technical hinge that determines return more directly than almost any other. The chemical and logistical reality of propellant and return vehicle readiness, where the mass of fuel and the reliability of production or delivery can decide whether leaving Mars is possible at all. Returning from Mars begins as a chemistry problem, A vehicle can be designed to rise from the surface, but it cannot rise without propellant, and propellant is mass. Mass is expensive to launch from Earth, expensive to land on Mars, and difficult to store for long periods in a harsh environment. This makes return the most demanding part of the mission architecture. A habitat can be made redundant and repaired. A return vehicle, once compromised, may not be replaceable on the timeline of a crew. The first humans on Mars may never return because return propellant and return hardware require a chain of successes that is harder than survival alone. Survival can continue with reduced capability. Return demands a full capability at a specific time. The basic need is to lift a crew off the Martian surface and place them into a trajectory that can rendezvous with an interplanetary vehicle or directly depart for Earth. Depending on architecture, Mars' gravity is lower than Earth's, which helps. The atmosphere is thin, which reduces aerodynamic drag during ascent. Yet these advantages do not remove the propellant requirement. Rockets need propellant to provide momentum. The amount depends on vehicle mass, engine efficiency, and target orbit. A return system must be capable of safe launch, even if the crew is fatigued and systems are partially degraded. Therefore, it must have margin, and margin means propellant. Propellant can be delivered from Earth as a storable fuel, or it can be produced on Mars using local resources. Delivering propellant from Earth is straightforward in concept, but punishing in mass. Every kilogram of propellant requires additional propellant to launch it from Earth and to send it to Mars. It must then be landed. Landing mass is difficult as described earlier. Therefore, delivering the full return propellant from Earth can dominate mission logistics and may exceed early launch capability. This is why many realistic mission plans consider in-situ resource utilization, producing propellant on Mars, often using carbon dioxide from the atmosphere and water extracted from ice. In-situ propellant production is attractive because Mars offers carbon dioxide as an abundant feedstock. If hydrogen is available from water, methane and oxygen can be produced through chemical reactions. Oxygen can also be produced from carbon dioxide by splitting it. These processes reduce the amount of propellant that must be carried from Earth. Yet they introduce a new dependency, a chemical plant that must operate reliably on Mars for months. The plant must run in the cold, dusty environment. It must manage compressors, reactors, pumps, and storage. It must maintain purity. It must be powered continuously. It must store the produced propellant without loss. If the plant fails, the return tanks remain empty. The plant cannot be treated as a minor add-on. It is a central system, comparable in criticality to life support. It must be deployed, connected, and started. It must run with high uptime. It must survive dust intrusion and temperature cycling. It must survive the occasional need to shut down and restart. It must also be protected against faults that could lead to leaks or explosions. A propellant plant deals with reactive gases and high pressures. Safety systems are required. Safety systems add complexity. Complexity adds failure modes. In a remote setting with limited spares, failure modes matter more. Water extraction is also a dependency if methane and oxygen production is planned. Mars has water ice in some regions, but extracting it is not trivial. The ice may be mixed with regolith, requiring excavation and heating. Equipment must dig, transport, heat, and condense water vapor. Filters and seals must handle dust. Heating demands power. The process must run for months to deliver enough water for both life support and propellant production if both draw from the same reservoir. If water extraction yields less than expected, propellant production slows. The mission then faces a schedule risk. The propellant might not be ready before the return window. Propellant storage is another quiet constraint. Some propellants are cryogenic, meaning they must be stored at very low temperatures. Cryogenic storage over months is difficult because heat leaks in and propellant boils off. Active cooling can reduce boil-off, but active cooling requires power and adds complexity. Mars nights are cold, but the environment still delivers heat through sunlight and through equipment operation, and the thermal gradients are difficult to manage. Storable propellants reduce boil-off concerns but may be less efficient or more toxic, complicating handling and safety. Each choice has trade-offs. A mission that depends on long-term storage must choose a propellant strategy that can survive months or years on the surface without unacceptable loss. The ascent vehicle itself must be maintained through the entire stay. Engines must remain functional. Tanks must remain sealed. Valves must not seize. Seals must resist dust. Electronics must tolerate radiation and thermal cycling. The ascent vehicle may be kept in a protective enclosure, but building and maintaining such an enclosure adds mass and complexity. A simple vehicle sitting exposed may be vulnerable to dust infiltration and temperature extremes. A complex vehicle protected by a shelter depends on the shelter's integrity and the base's ability to maintain it. Either way, a return vehicle is not a static object. It is a system that must be preserved in readiness. If it degrades, return becomes uncertain. The chemical nature of propellant also makes testing difficult. A tank can appear full and still have contamination. Contaminants can damage engines. A valve can appear closed and still leak slowly. A leak can be small and yet significant over months. Therefore, propellant systems must be monitored continuously with sensors. Sensors can fail. Calibration can drift. A crew must maintain the measurement chain that assures propellant quality. This is another way the mission depends on maintenance and attention, as discussed earlier. Return requires that all these details remain within safe bounds at the time of launch. The timeline of propellant production is tied to launch windows. If propellant production starts late or runs slower than expected, the return window can arrive before tanks are full. In that case, the crew cannot depart safely. Waiting for the next window means waiting years. That wait consumes life support supplies and increases radiation exposure. It also risks further system degradation. Therefore, propellant readiness is not only a condition for leaving, it is a condition for leaving on the correct schedule. A mission can survive without return readiness for some time. It cannot survive indefinitely if food and consumables are limited, and it cannot keep return hardware pristine indefinitely if maintenance burden and degradation continue. This is why many conservative architectures suggest producing the return propellant before the crew arrives. A robotic mission can land the propellant plant, start it, and confirm that tanks are full. Only then does the crew depart Earth. This reduces the one-way risk, yet it increases program complexity and requires multiple successful cargo missions. If the pre-production campaign fails, the crewed mission is delayed by years. This can threaten program continuity. If the crew still flies without full pre-production, then the mission accepts a one-way risk, because the crew may arrive to a propellant plant that fails after partial production, leaving insufficient fuel to return. Even if propellant exists, launching from Mars is not a guarantee. The ascent vehicle must ignite reliably. It must reach the correct trajectory. It must rendezvous with an orbiting vehicle if that is part of the plan. Each step is a high-consequence event. A base might keep the crew alive with degraded systems, but it may not be able to support the precise and power-intensive operations needed to prepare an ascent vehicle. Check systems, load cryogenic fluids safely, and perform launch procedures in a limited time window. A mission could therefore reach a state where survival continues but launch readiness does not. The return propellant problem also links to ethics and realism. A mission that cannot guarantee return may still be proposed if the goal is permanent settlement. Yet the title's focus is on why the first humans may never return, even when return is intended. The propellant chain is one of the clearest reasons. It requires either hauling vast mass from Earth through difficult landings or relying on complex chemical production in a harsh environment. Both paths contain failure points. A failure can leave the crew alive but without fuel. Without fuel, there is no ascent. Without ascent, there is no return. No amount of courage changes that. This region therefore brings the inward path into the core technical hinge. Return is a chemical requirement measured in propellant mass, production reliability, storage stability, and system readiness. In situ propellant production can reduce Earth launch mass, but adds a critical dependency on months of successful surface chemistry and power. Delivered propellant avoids the plant but increases landing mass and logistical complexity. Propellant storage is difficult over long durations, especially for cryogenic options. Ascent vehicles must be preserved in readiness through dust and thermal cycling. The return window imposes a schedule that punishes delays. These constraints make return fragile in early missions and provide a realistic pathway by which a crew could become stranded even if the base remains otherwise survivable. From this propellant hinge, the inward path moves into the ascent and rendezvous phase itself, where the act of leaving Mars introduces another set of narrow margins and reliability requirements, and where a single failure can convert stored propellant and planned schedules into an irreversible stay. Leaving Mars is not the mirror image of arriving. Arrival is a descent through a thin atmosphere with heat and uncertainty. Departure is an ascent from a dusty pad into a sky that offers little margin for correction and little opportunity for rescue. The ascent must work on a single attempt, because a failed launch can destroy the vehicle and consume the propellant that cannot be replaced quickly. Even a successful ascent can fail later if rendezvous and departure steps do not proceed as planned. This is another realistic reason the first humans on Mars may never return. Return is a chain, and ascent is one of its narrowest links. A Mars ascent begins with a vehicle sitting in a hostile environment. Dust has settled on surfaces and into crevices. Temperature cycles have expanded and contracted seals and joints. Electronics have been exposed to radiation. Tanks have held propellant for months. Valves have remained closed and must now open precisely. Ignition systems must spark. Engines must produce stable thrust. The vehicle must rise cleanly and align to a guidance program. On Earth, launch operations rely on large teams, extensive ground support equipment, and the ability to replace components after inspections. On Mars, the support is limited. The crew must conduct checks with the tools available, often in suits or from within a pressurized habitat. Some checks cannot be as thorough as on Earth. The mission, therefore, depends on design reliability and on the preservation of a vehicle through long exposure. Ignition reliability is central. A rocket engine must start cleanly. In many engines, propellants must flow in the right ratio and at the right pressure. If the ratio is wrong, combustion can become unstable or temperatures can exceed material limits. If a valve sticks, a pump can cavitate, or a sensor fails. The engine may shut down or explode. A safe design includes redundancy and robust ignition procedures, but the reality of rockets is that ignition is a complex transient event. On Mars, a single engine failure at liftoff can be unrecoverable if the vehicle is not designed to tolerate it. Therefore, return architectures must either accept that ascent is a single point of failure or include redundant engines and abort capabilities. Redundancy adds mass. Mass increases the propellant required. The propellant requirement is already tight. This tension is part of why ascent is so difficult to guarantee. Guidance and navigation are also critical. The vehicle must follow a trajectory that places it into a stable orbit or into a suborbital path that reaches an orbiting vehicle for rendezvous. The guidance must account for atmospheric drag, which is small but not zero, and for winds, which can perturb the vehicle. The vehicle must maintain attitude control. Attitude control systems use thrusters, reaction wheels, or other mechanisms that must function reliably. A failure can lead to loss of control and breakup. On Earth, range safety can terminate a vehicle. On Mars, the consequence of a loss of control is simply impact and loss. There is no rescue system on standby. Mars orbit rendezvous adds another layer of precision. Many realistic return plans involve an ascent vehicle reaching Mars orbit to meet a larger interplanetary vehicle that remains in orbit. This reduces the mass that must be landed, because the interplanetary vehicle can stay in space, yet it adds the requirement of rendezvous and docking. Rendezvous requires accurate orbital insertion, accurate tracking, and accurate timing. It requires propulsion for orbital adjustments. It requires sensors and guidance for final approach. Docking requires a compatible interface and mechanical reliability. A docking failure can leave the ascent vehicle with limited life support and limited propellant. A crew can be alive in orbit and still be unable to return if docking fails and the ascent vehicle cannot sustain them or cannot perform a second attempt. Tracking and navigation on Mars rely on a combination of onboard inertial systems and external references. External references can include orbiting satellites, surface beacons, and star trackers. Each system can fail or degrade. Star trackers can be confused by dust or glare. Sensors can drift over time. Communication delays mean Earth cannot manage rendezvous in real time. The crew and the onboard systems must execute the plan with autonomy. This returns to the earlier theme: critical operations must work without immediate ground control. Any error in timing can create a missed rendezvous, and missed rendezvous consumes propellant. In a system with limited propellant margin, repeated attempts may not be possible. The ascent also depends on the health of the crew. Launch from Mars involves acceleration and vibration. A crew member recovering from injury or weakened by long-term exposure may not tolerate launch well. If a medical event occurs during ascent or rendezvous, treatment capability is limited. This is another way return can fail even when the vehicle works. A mission can have hardware readiness and still lose return feasibility because the crew cannot execute the sequence safely. The ascent pad environment is another subtle risk. A vehicle may sit on regolith or on a prepared surface. If the surface is unstable, thrust can erode it and create debris that damages the vehicle at liftoff. A prepared pad reduces this risk, but building a pad requires equipment and time. In early missions, pad preparation may be minimal. The vehicle's engines can blow dust and small rocks at high speed. This can damage nearby equipment, including the habitat and power systems. Therefore, base layout must keep the ascent vehicle separated from critical infrastructure. Separation requires mobility and site planning, which depends on landings being precise and on terrain, allowing safe spacing. Return chains also include the possibility of staging. Some plans involve launching a small ascent vehicle to orbit where it meets a habitat module that provides life support for the return. Others involve using the ascent vehicle itself as part of the return system. The more complex the staging, the more interfaces exist, and each interface is a potential failure. Valves, seals, docking rings, electrical connectors, and software protocols must all work. Each of these must be preserved for months on Mars or in orbit. Each must be tested. Testing consumes time and resources. A base under strain may reduce testing, increasing risk. A single failed connector can prevent power transfer. A single seal failure can prevent pressurization. The crew can be alive and still unable to use the return system if an interface fails. The rendezvous phase also depends on orbital assets. Communication relays and navigation satellites in Mars orbit can improve safety. Yet these satellites must exist and must function. They must be launched and maintained. If a critical relay fails, communication between orbit and surface can degrade. If a navigation aid fails, rendezvous becomes harder. Redundant satellites increase robustness, but increase cost and complexity. Early missions may have limited orbital infrastructure. This makes ascent and rendezvous more demanding. If ascent fails, the outcome can be irreversible. A destroyed ascent vehicle cannot be repaired quickly. Propellant consumed in a failed attempt may be gone. A second ascent vehicle might not exist. Even if a spare exists, it may require new propellant, which may take months to produce, and the return window may not wait. Therefore, ascent is not only a technical event, it is a point where the mission can switch from return possible to return impossible in a short time. This is one of the few phases that can produce a decisive outcome quickly. The crew may remain on the surface with a functioning habitat, but the path home is lost until a new vehicle can be delivered, which is tied to distant windows and program capability. Even if ascent succeeds, a failure in rendezvous can produce the same result. A missed docking can strand the ascent vehicle in orbit with limited supplies. In some architectures, the interplanetary vehicle might be able to maneuver closer, but propellant limits and timing limits exist. If docking cannot be achieved, the crew may face a fatal outcome in orbit rather than a long stay on the surface. To avoid that, mission designs aim for robust docking systems and multiple attempts. Yet each attempt consumes propellant and life support. Therefore, a mission must balance redundancy with mass limits. Again, early missions sit near the edge. This region therefore treats ascent and rendezvous as the narrow mechanical bridge between survival on Mars and return to Earth. The ascent vehicle must remain healthy through long exposure, start reliably, and follow precise guidance. The crew must be fit enough to execute the operation. Rendezvous must succeed in an environment with limited real-time ground support. Interfaces must work. Orbital infrastructure may be limited. Any failure can be irreversible within the mission timeline. These facts make return fragile even when everything has gone well up to that point. From this narrow bridge, the inward path moves to a final external constraint that closes many imagined escape routes, the limited abort options and the realistic impossibility of rapid rescue. This next region shows why Earth cannot simply send help quickly, and why the absence of that option changes how risk is carried by the first crews. In many human stories, danger is softened by the thought that help can arrive. On Mars, help arrives on orbital schedules rather than on urgency. The distance between planets, the launch window cycle, and the need to land heavy cargo combine to make rescue slow and uncertain. There is no equivalent of a rapid medical evacuation. There is no quick delivery of spare parts. There is no easy retrieval of a stranded crew. The absence of rescue is not a dramatic claim. It is a consequence of physics and logistics. This absence changes the meaning of every risk in a Mars mission, because it removes the final safety net that often exists, even in difficult environments on Earth. A rescue mission requires the same basics as a primary mission. A vehicle must be launched from Earth. It must travel to Mars. It must enter, descend, and land. It must deliver supplies or a return capability. It must do so within the constraints of mass and launch capability. These steps cannot be shortened below certain physical limits. Interplanetary travel requires months. Launch windows constrain departure opportunities. Even a high-energy trajectory cannot produce a rescue in days or weeks. Therefore, when a crew on Mars faces an emergency, the soonest meaningful help from Earth is often too late for immediate survival needs. The window constraint is the most decisive. If Earth and Mars are in an unfavorable alignment, a launch to Mars may require more energy than the available rockets and spacecraft can provide, or it may require a longer travel time than an emergency can tolerate. Even if a launch is technically possible, the arrival could take many months. A crew in immediate danger, such as one facing a life support failure, cannot wait many months. Therefore, the mission must be designed so that immediate survival does not depend on outside rescue. This is why redundancy, spares, and pre-deployed assets are emphasized. Rescue is not a plan. It is a long-horizon possibility, and only in some scenarios. Even when a launch window is open, rescue remains complex. The rescue payload must be landed near the crew or must be capable of reaching the crew. Precision landing for heavy cargo is difficult. A rescue lander that arrives hundreds of kilometers away may not be useful if surface mobility is limited. A rescue mission could also aim to place a vehicle in Mars orbit for rendezvous, but that still requires that the stranded crew have an ascent vehicle and propellant to reach orbit. If the crew's problem is that the ascent vehicle is damaged or unfueled, an orbital rescue is not sufficient. The rescue mission would then need to land an ascent capability or deliver the means to repair or refuel, which returns to the same difficulties of landing heavy systems. Communication delay adds another dimension. In a crisis, Earth cannot direct operations in real time. Earth can provide advice and analysis, but the crew must act. A rescue plan would have to be executed largely by the crew, using delayed guidance. This is true even for a rescue mission that reaches Mars orbit. Docking and transfer operations would still be carried out by onboard systems and crew with autonomy. Therefore, rescue does not remove the need for crew competence under stress. It only adds distant resources, and it adds them late. The impossibility of rapid rescue changes risk tolerance. On Earth, a risky operation can be undertaken with the knowledge that emergency services exist. On Mars, each risky operation consumes margin, because the consequence of failure cannot be offset by quick outside help. A crew may therefore choose caution more often, delaying repairs or external tasks. Caution can reduce immediate risk, but can also allow long-term problems to grow. If a power system is degrading, delaying external maintenance might preserve safety today but reduce survival later. This creates a difficult pattern of decisions. The crew must balance short-term safety against long-term base health in an environment where both are essential and where rescue is not available to correct a mistake. The absence of rescue also interacts with program continuity. A rescue mission is not only a technical effort, it is a major program commitment requiring launches, vehicles, and sustained funding. If a Mars mission encounters serious problems, the political and economic ability to mount a rescue may not match the urgency. This is a sensitive point, but it is a realistic one. Space programs operate within budgets and public support. A rescue mission could be attempted, but it would still take time, and it would compete with other priorities. The crew cannot depend on such a mission. In the way a sailor depends on Coast Guard services, the crew must depend on the base. Abort options during transit are also limited. Before arrival, some trajectories allow a spacecraft to loop back to Earth without landing, but the loop still takes months, and it assumes the spacecraft remains healthy and life support remains stable throughout. If a life support problem occurs during outbound transit, the crew might not have a rapid way home. A free return style trajectory, if available, might still bring them back only after a long time. Meanwhile, the crew must survive the problem, therefore abort in interplanetary flight is not an escape. It is a different long mission with its own hazards. After landing, abort becomes even more constrained. Leaving Mars requires an ascent vehicle and propellant. It also requires that the return window is open, or that the return vehicle can take a higher energy path. A crew cannot simply decide to leave because of a problem unless the ascent system is ready. If the ascent system depends on propellant production, that propellant must exist. If the ascent system is damaged, it cannot be replaced quickly. Therefore, abort from the surface is often not possible in the way abort is possible from low Earth orbit. The crew's main response to problems is to stabilize the base and endure. This endurance is influenced by supply margins. A base can include extra food, extra water, and extra spare parts to cover delays. Yet margins add mass. Mass increases landing difficulty. Therefore, margins are limited. In early missions, margins are likely to be tight because launch capacity and budget are limited. Tight margins mean that a missed return window could push the base toward exhaustion of consumables. A rescue mission might then be proposed, but it would arrive on the same slow timescale. The crew could still run out of essentials before help arrives. This is the harsh logic behind the phrase "may never return." It is not a claim that every mission fails. It is a statement that certain failure modes cannot be repaired within a humanly relevant timescale. The absence of rescue also shapes the psychological landscape. Knowing that help cannot arrive quickly changes how risk feels. It can motivate discipline and careful procedure, but it can also increase stress and conflict. A crew may feel trapped by the geometry. That feeling can be amplified if the return schedule becomes uncertain. Uncertainty about return can erode morale, and eroded morale can increase operational risk. The mission therefore carries a psychological hazard tied directly to the absence of rescue, not to personal weakness but to a realistic appraisal of circumstance. This region therefore closes the external door gently and clearly. Rescue is slow because of distance, launch windows, and travel time. Landing rescue cargo is hard because of entry, descent, and landing constraints and site precision needs. Orbital rescue depends on ascent capability that may be the very thing that is missing. Abort paths are long and limited. Programmatic realities can further limit rescue capacity. These facts mean that early Mars crews must assume that their survival depends on their base, and their return depends on their base plus a functioning ascent and return chain at the correct window. If that chain breaks, the crew may remain alive but beyond rescue and beyond return within the time frame of the mission. From this closed-door constraint, the inward path moves to the final synthesis. The concluding region gathers the technical and human reasons into a calm, realistic outcome, explaining how early missions can become non-returning without exaggeration and how the risk can be reduced but not eliminated. The first humans on Mars may never return because Mars missions are not single events. They are long systems that must remain coherent across distance, timing windows, environmental stress, and human limits. Return is not one promise. It is the final step of a chain that begins before launch and continues through cruise, landing, surface survival, propellant readiness, ascent, and interplanetary travel back to Earth. Any link can weaken over time. Some links, once broken, cannot be repaired within the schedule enforced by orbital mechanics. In that sense, non-return is not a dramatic scenario. It is a realistic outcome for certain combinations of failure, delay, and degradation in early missions, especially if redundancy and resupply capability remain limited. The outermost constraints remain the simplest. Earth and Mars are far apart and their distance changes. Communication is delayed. Advice arrives late. Rescue arrives too late for many emergencies. Launch windows create long intervals when return is not feasible. These physical constraints turn time into a resource as critical as oxygen. When a mission plan depends on leaving Mars on a particular window, it depends on remaining functional until that window. If the mission is forced to wait for the next alignment, the wait is not a small extension, it is years. Those years must be survived on the surface with finite supplies and aging machines. Even if a crew stays alive, extending the timeline increases radiation exposure, increases maintenance load, increases psychological stress, and consumes food and consumables. Therefore, the geometry of the solar system can convert a short delay into a fundamental change in mission outcome. The arrival phase concentrates risk into minutes, entry, descent, and landing on Mars is hard at human scale because the atmosphere is too thin to slow heavy payloads easily. A mission must land habitats, power systems, spares, and often return-related hardware. Each landing is a gate that must succeed. A failure in a cargo landing can delay a crewed mission by years. A failure in a landing that damages return hardware can remove the return path entirely. Even when landings succeed, dispersion can separate critical assets, increasing operational burden and risk. The thinness of the atmosphere and the need for propulsive landing drive mass and fuel demands that tighten margins. This is why early architectures depend on pre-deployment and proof of systems before human arrival. Yet pre-deployment itself increases the number of critical landings and the length of time systems must survive unattended. Once on the surface, Mars offers no support. Pressure, oxygen, water, and temperature must be maintained by a habitat that functions continuously. Dust and cold stress every moving part and every seal. Radiation continues to accumulate. Life support must close loops for air and water and manage food stores without resupply. Power must remain stable through dust events and long nights. Maintenance must be performed by the crew with finite spares. A base can be designed with redundancy, but redundancy adds mass, which increases landing difficulty, which increases failure risk. The mission therefore sits in a balance carry enough margin to survive failures, but not so much mass that landing and deployment become unmanageable. Medical reality adds another constraint. Evacuation is not available. Some injuries and illnesses that are treatable on Earth can become disabling. Medications have finite shelf life. Surgery and intensive care are limited. A single medical event can reduce crew capability and increase maintenance risk. Human factors then amplify these pressures. Sleep disruption, isolation, conflict, and cognitive load affect attention. Attention affects procedural quality. Procedural quality affects safety and system health. Over long time, a crew can become exhausted, a base can become fragile. Return then becomes less of a planned step and more of a question, whether a crew and their machines remain capable of executing a demanding ascent and a long return flight at the precise time the window allows. Return itself is the hardest link because it is a chemistry and reliability demand. Propellant must exist in sufficient quantity and quality. Propellant must be stored without loss. A return vehicle must remain preserved in the Martian environment for months. If propellant is produced on Mars, a complex chemical plant must run reliably under dust and cold, powered continuously, without major breakdown. If propellant is delivered from Earth, enormous mass must be landed. Either way, return depends on heavy systems operating at high reliability. When return depends on in-situ production, a single long outage can make tanks incomplete at the window. When return depends on a single ascent vehicle, a single ignition failure can end the possibility of departure. Rendezvous and docking, if required, add another narrow margin. These are operations that cannot be repeated many times because propellant and time are limited. Rescue remains the final absent option. Even if Earth can mount a rescue mission, it arrives slowly and must still land safely and reach the crew. In the early era of Mars exploration, the infrastructure for repeated launches and rapid replacement will not exist at the necessary scale. Therefore, a crew that loses its ascent vehicle or cannot produce propellant may remain alive in its habitat, but be unable to leave until a new mission can deliver a new ascent capability, which may be years away and may never come in time. This is how a mission intended as a round trip can become non-returning without a single cinematic moment. The realistic conclusion is not that return is impossible. It is that return is fragile in early missions and depends on a long chain of successes across systems that have not yet been proven at human scale on Mars. Risk can be reduced by building redundancy, by pre-deploying and verifying return propellant and hardware before sending humans, by investing in robust power such as nuclear systems, by improving landing capability for heavy payloads, by expanding orbital infrastructure at Mars, and by designing habitats that can be shielded with local materials. Risk can be reduced by expanding spare inventories and fabrication capability, though mass limits remain. Risk can be reduced by careful crew selection, training, and psychological support. These measures move a mission away from the edge. They do not remove the fundamental constraints of distance and timing. In a calm final view, the first humans on Mars face a world where survival is possible but not forgiving. The interplanetary gap makes help late. The window cycle makes waiting long. The thin atmosphere makes landing and heavy logistics hard. The surface environment makes life support and maintenance continuous and delicate. The return requires propellant and reliability that must be preserved through months of exposure and stress. Under these conditions, a crew can arrive with a return plan and still lose return capability through a chain of small failures, delayed schedules, and system degradation. The crew may remain because they cannot leave, not because they choose to stay. This is the realistic science behind the idea that the first humans on Mars may never return.